So I knew that we were completely scooped, both the timing as well as the contents, I think. Yeah. But the other part really surprised is how they can get to this thin layer. Getting to the fully quantum versions, you need two more conditions needed. One, that you need an even stronger magnetic field, going over all the kind of defects and getting into fully quantum limits. And second part is basically you have to really confine the electron in the 2D. He reported that atomically thin TMD, that TC가 changes as you go to low dimension. There's more of the fluctuations, and TC tend to be dropped because of these fluctuations. And then you naturally think that how he made this sample, right? Guess what? He used a Scotch tape.
This week, Xinghui and Misha speak with Harvard physicist Philip Kim, whose career has helped define the physics of low-dimensional materials, from cuprate superconductors and carbon nanotubes to the earliest graphene devices. Kim walks us through quantum transport, the Hall and quantum Hall effects, and shares some of the stories behind these discoveries. Please welcome Philip Kim.
Cool.
You spent your career shrinking the playground for electrons and somehow discovering more freedom every time. Was that the plan, or did the physics keep pulling you forward, whether you intended it or not? Like, what was the guiding line that you feel like made you move from carbon nanotubes to graphene?
Yeah. Well, the first question itself is very hard.
It's a bit of a historical context.
Yes, I think there is a bit of a historical context. I'm not sure. It was a somewhat kind of planned or that natural that inclinations in that directions, I would say. There was actually kind of some funny stories that probably should getting back to my PhD times that. So I did PhD here at Harvard, but my lab was across the road at the Oxford Street. It was students that were working with Charles Lever. He's known to be back then also the scientist who just kind of initiate this nanoscale science and technology.
Is it the chemical department? Or
so he's in the chemistry department. I was in the applied physics the program students, like you, right? But then because Charlie was involved also into the applied physics, the program, so I think choosing him was kind of also possible. And when I came here to do my PhD, I was interested in doing the back then, one of the hottest materials, high temperature superconductor, cuprate.
Yes.
And also, I was drawn also the scanning probe microscope, especially STM. And Charlie was kind of one of the persons that are doing this both kind of in his program. So I went to his lab and hoping that I want kind of do something. And indeed, the first project I did in his lab was a high temperature superconductor and study about the flux line lattice structures using so-called the beater magnetic decoration technique. That's basically sprinkle the ion particle and look at where the vortex structures look like, and from there you can figure it out property of the magnetic flux line in cuprate, which was a very hot topic back then.
What material was that?
That's interesting. That was a bismuth, strontium, calcium, copper oxide, known as BISCO. So you will hear that interesting study later, yes. Right? So that was my first project. I worked in his group, and the Charlie's research style back then was kind of interesting. That he's been kind of more of the adventurous various different material system, and the cuprate is one of the hot topic then, and he find that as kind of quite exciting. He worked on there, but after one summer, I worked with him that we made the nice PRL paper, my first PRL paper. I was very proud of. But then he said, "All right, that's probably good enough. I'm going to move away from there." So I was now then kind of stationed to the another subgroup that now working on the STM. So anyway, that I started kind of work on the STM that I was kind of planned to, but not on the cuprate. And the material that they've been working on is some systems on the charge dense wave in very strange materials. It's a very difficult to even pronounce a name in the beginning. The material name is a transition metal dicharcogenide. So by now it's known as a TMD and well-known 2D semiconductor. But back then, you see that I start to regret, why I just kind of started working the chemistry group and working this compound. Maybe so long to even remember, right? So that's kind of the project I worked on in his lab. And we also made very interesting papers out of it. But then guess what? He said, after the paper that published in Science, he said, well, that's good enough. Then I'm going to
You moved
Yeah.
again.
go away.
It's quite surprising.
Quite surprising, right?
Because usually people are like, yeah, we just
we need to
Well, gold mine right now.
Yes.
Let's
well,
keep
there's a
digging.
part. I
strike
think,
the iron while it's
there are
hot.
always people just worked before me that for a few years on that subject. Cuprate was like that back then. Hong Ji-dai, who was my predecessor, worked on there for 4-5 years, and he
Wow.
graduated and moved away. So I was closer of that project. Same thing of this charge density wave in the TMD. There
That
are
sounds lucky
people-
in
yeah.
a way
Yeah.
because you
I
get
mean
to
closer,
be
right? Yeah, but and then he said, "All right, so you know that now that this nanotube becomes kind of quite important in the community, so why don't you go and study about nanotube?" So actually, I just moved to my study to the nanotube. So
and the methods were transferable between the different systems, or you had
not
to
really,
restart
not really.
every
I think
time
I
with
think
a new project.
ferromagnetic decoration is nothing to do with STM.
Yes.
And well, nanotube and the CDW was STM study, so it was already connected. But anyway, so by the time that I graduated, and then I had enough paper, but I have to write the thesis. A thesis need a title and coherent theme, right? So I have just kind of this several projects. I just consult with my friends sitting into the physics department back then, ask that, hey, so what should be the title of my thesis, you think? I think I have this problem that I have enough the result, I can just make the thesis, but it's a very incoherent thing to me. And he was saying to me that, that's why I told you don't go to the Charlie's lab and see what you have here. So it was not too useful. But then after that, I actually got the revelations. So the cuprate is very anisotropic, and a lot of physics is basically in the kappa-oxygen plane. Likewise, the vortex is going through, seeing a lot of the 2D kappa-oxygen plane and connect them together. So often, the right way to describe this system is 2 + 1 dimension, right? STM study on charge density wave on this TMD is a surface study. So basically kind of all the things in the 2D. And nanotube, of course, 1D, right? So once I realized that, I get the title of my thesis. So title of my thesis was, I think, physics and applications of load measure system. Well, that is basically title. And in some sense, I was drawn into this load measure material by just a will of my the PhD advisor. But somehow I actually liked it. And that's kind of how it got started out, all this low dimensional physics.
It's actually a really nice story. But do you remember what compelled Charlie Lieber back then to move between these fields? Was it initial theoretical studies, specific papers that drew his attention?
Right. I think he has in the retrospect, he has kind of a very good intuition, so instinct. I think that what could be a good system to explore. He has a reasonable size of group, so he could kind of move around the group. His research style is a little bit of the hopping through the different subject and the navigate through that kind of his interest in that way. So what he did after I kind of left his group is also kind of rather different directions. He worked on the nanowires and then nanowire into some of the nanomedicines. And I think the direction is kind of really changing. And everybody that walked through him along the time make sort of tangential move. So eventually that this group spans kind of really wide range of the science, not only physics, not only chemistry, but even biology, right? So it was kind of his style. I'm not sure that whether I can follow his style in that way, but I certainly, it is one example of scientists I've been seeing that, somebody's interest actually varies over the time with the really broad ranges, physics, chemistry, and biologies. So I think that's kind of one good example that how the interest can span in that way and can be successful. Although I think we've been observing the past a few years, I think was kind of quite challenges for him. But yeah, anyway, that before then.
So that you mentioned about the low-dimensional systems. So what, usually in your talk, you also start from Flatland, the novel by Abbott.
Yes, yeah.
Did you read it already, like at that time? That
No,
gave you some ideas, or did it happen?
I think that's a much later time. I think when is actually I read that novel many years later after even the Nobel Prize or something like this. I think it's at the time that when I prepared it, one of the public talk. I think it's something like that 12 years ago, and somebody mentioned about this novel. So or I knew about the novel, but anyway, I want to use that clip or the part of the novel into the public talk. So and I actually compared that. I have to read this. So that's a time. The going back to this Flatland or that kind of graphene research, actually that has that kind of different motivations how it got started out. I think that's kind of something also I can share throughout this type of informal chat.
Yeah. Oh, that would be great. But we can stay a bit more with your biography. I suppose you did a postdoc after your PhD. Where did you do your postdoc? What did you work on? Did you have any choice in what you worked on?
Okay, so that's exactly the right topic that kind of getting there. So after Charlie's group, that I thought kind of I want to do something different. I wish to do something more kind of physics or device oriented. I think that's kind of something that I always am before when I was sitting at the other side of the road here. So I applied a few postdoc positions, and then lucky enough that I started to work with Paul McQueen, who was back then at the Berkeley. So I worked with I joined his group, and he's been back then known as just doing a lot of the interesting mesoscopic physics style of the measurement in low-dimensional system. Back then, the low-dimensional system can be either two-dimensional electron gas in semiconductor heterostructures. He worked on quite a bit this quantum Hall physics back then. And then he was just one of the pioneers that worked on nanotube. So there are a few groups, including Paul McQueen and Case Decker and the Delft. They've been just competing each other to just kind of demonstrate interesting quantum transport through the nanotube. So that's kind of the something that I got excited about, and I joined because I worked on the nanotube as the last project that during my PhD was kind of good pitch.
Did you try to go to 0D or like the
quantum dots? Ali Visatos, Berkeley could have been a choice.
It could have been choice, but Paul actually did some part of this 0D things. One nanotube is 1D, but he also did 0D transport through the buckyball and some nanocrystals. So that molecular electronics, and that's kind of one part. Luckily, I didn't go that direction. I think that 1D is enough.
He's also very successful.
But it's a very interesting story. So when I joined the Paul's group, the first the lunch that I had with Paul, and Paul took me out for the kind of lunch, and then discuss. Okay, so what do you want to do? The study. So before I joined his group, I just kind of studied his group's work, and I thought, so I want to do now. No one just called me the chemist, but I want to do that really something that deep into physics. So quantum Hall physics is very deep. So I was kind of thinking about some interesting problem. What can I do in the quantum Hall? But I have kind of not much of knowledge in quantum Hall, right? So I thought, that the maybe two-dimensional electron gas applying the magnetic field and form the Landau level. But at the same time, if you make some sort of periodic structures and try to create the electronic band in the superlattice form. It could be interesting.
Mm-hmm.
So I just kind of that, oh, this is something I've been thinking about. And Paul just kind of looked at me and then, Philip, you didn't read a lot of papers in this field. Right? And then, the idea you just kind of mentioned is very interesting and exciting, but has been tried out many years. And that is exactly that this hope shutter butterfly problems, and people have been trying for many years, right? I mean, they would. I think he explained to me that, well, that several methods people tried out, it didn't go too far, right? Because of various reasons. So it was shut down at once, right?
But it shows that you have good intuition because you're reinventing the same good question.
And then Paul asked, oh, yeah, so Philip, you're coming from the chemistry group, and you must actually thought about how to make the graphene. And that's kind of what you mentioned. And I know, though, I think first that I got hurt because I know that when physicists say that, you're coming from chemistry group, and I know that what it can be often mean.
Make us new materials.
So I have to define, yes, I worked with Charlie, but that my background, so I worked I get the degree in applied physics. So I know the physics. Defend myself. I asked him that, why is interesting the graphene? By the way, that graphene has been known for the community, especially working on the nanotube for a long time. Part of the reason the graphene is known is when you explain the electronic structure of the nanotube, you want kind of first to show that graphene electronic structures, which actually was calculated in already 1948 or something like that, when people try to Phil Wallace, they tried to figure out the graphite band structure. That was a time that already figured out.
So the following Dirac equation. Was
using the term of the Dirac equation was not there popularly, although there are few people recognize this the Dirac spectrum, Dirac the spectrum and Hamiltonian, including Duncan Haldane many years ago, but it was not really popular description at all. But nevertheless, graphene band structure has been known, and the word of the graphene therefore is known, because to try to understand the nanotube, graphene is starting point. So when Paul asked me about the graphene, of course I understand graphene and their band structures and things. But I was kind of curious why he's interested in the graphene. And there's a kind of reason for that. It was, I studied postdoc in 1999. And the 1 year before then, 1998, there was a kind of rather interesting paper that published by the very respectable Japanese theorist named Junei Ando. Published the paper. The title contains that several keywords: the pseudospin, Betty phase, and the nanotube. Nanotube here means basically graphene that he did calculation, and he's the one. His paper actually shows that indeed those kind of pseudospin provide the Betty phase into this Hamiltonians in the right way, make the electron mean free path in nanotube is extremely long.
Did someone try to cut these nanotubes,
fold it,
break them in a certain sense?
Yeah. So I think that's interesting. Indeed, some people did try after discovery of graphene
with fib. Or
no, I think chemically.
Yes.
Hongji Dai that I mentioned before, my predecessors at Harvard, he's the one that professor in the chemistry and who first demonstrated cutting the nanotube to make graphene sheets.
Wow.
But that was after graphene becomes kind of more popular.
Right.
So the Paul somehow read this paper. That paper, the Ando's paper, was published in Japanese Journal of Physical Society. It was not necessarily well known to the many people, but Paul somehow picked that paper and immediately saw that importance of the paper, and he did actually use that paper to calculate something or reinterpret something in his nanotube data and make the nice paper. And that's a time that I joined his group. So naturally, you can see that his interest is okay. Maybe not only just kind of look it through the nanotube, making graphene itself can be quite interesting. So he was suggesting me that work on it. How about the making graphene, part of the reason is there are a lot of interesting stories there. So through him that I was introduced to this interesting graphene physics, and that was a part of my postdoc project, which didn't go too well.
Sounds
Tell
very
us more.
challenging.
Tell us more. What were your approaches to making graphene?
So the way that we tried out is that so back then how the people just make the nanotube device is nanotube is grown by kind of some chemical synthesis or some sort of I think some oscillations or the chemical process, a various different way or that one can produce nanotube. Usually nanotube is coming out the suit. So you have to make the individual nanotube device. You just take the suit and put into the some alcohol or some solutions and sonicate it. And then that sonication will break this nanotube into pieces.
So you take soot, you sonicate it in the
And
suspension.
then,
and
suspension nanotube. Yeah. So I think
doesn't need to be at a certain, what are the ingredients to, how do you control, like, what's the size of the nanotube, the yield?
I think that, you need a good chemist who can produce this time the higher purity. But then once you spread it onto the substrate, silicon substrate, you can just kind of look through the STM, not STM, SCEM or the AFM. You can find where nanotube is. So basically, if you just control this sonication well, you can separate the nanotubes more like the close to individual way.
Did people also measure the transport properties?
Yes. So that's kind of how that Paul McEwen's group and then other groups back then tried to make the device out of it. So that technology has been there, right?
What was the main motivation for nanotubes to use?
That was back then one of the most important problems. That in terms of physics, one-dimensional electron system is very unique, and there are a lot of the well-known exact solutions that do exist in one dimension.
Like Luttinger liquids.
Luttinger liquid is a good example, right? The 1D localization is very strong also. So there are many quantum phenomena you can just look through into the one-dimensional system. But also technologically, I think a nanotube comes with a various different band gap and depends on the chirality of nanotube. If you can imagine that the scaling down to the channel, the nanotube is one of the candidates and still remain as one of the important candidates into the industry that if you really scale down the transistor to the small scale.
And what happened to the field of nanotubes these days? So I know it was pretty high.
No. I think that's so the highest peak of the nanotube is probably late 90s and beginning of 2000-ish. And there are a lot of the prominent groups and a lot of people's work on nanotubes. That more or like the giveaway to the graphene when it comes with the 2004 and 2005. Ever since that nanotube study, at least in the physics communities, dropped down quite a bit. I mean, there are still good and important studies there, but not the level that what used to be in, say, that 30 years ago.
Is it more like a physics toy or something came out of that research on nanotubes?
It is probably more physics side. Part of the reason is one-dimensional physics is kind of interesting, but there's well-known solutions there, and then more like they explore everything's there. Then there's not much of the phase space remains anymore, right? So I think that's kind of what I feel like, right?
To 2D,
So that's kind of low. The problem with the low dimension is sometimes the phase space is too limited, right? So that's a part. But it's interesting that speaking of the nanotube, there are still that a lot of people is working on the nanotube. Not anymore the many physicists, but a lot of material scientists and chemical engineers, for example. And worldwide now, the production of nanotube is 100 tons and even kind of a lot, more than that.
What is it mostly used for?
I think I heard that it's used as some sort of composite elements, or that can be added into the electrical batteries. And there are quite of the applications out there. Anyway, kind of winding back to the time. So that's kind of how the nanotube is being prepared. So you can imagine that graphene can be prepared in similar way. So the way that I approach it is very similar way that I get the graphite powder and sonicate it, and spread onto the silicon substrate
Yes.
and look through the very thin pieces. And then one can locate it in piece and just kind of make the electrical device. One can study about the electrical properties of this type of studies. So up to there, it was reasonably successful, and we did see that transport can happen and gate dependency is happening. I think that's an important part of mesoscale device. So if you just put another metallic plate underneath, and using that, you can control the carrier density continuously. That's like that semiconducting device. That's an important part. And that worked it out. The downside that we saw that is that sample is rather disordered. So there's not much of an interesting quantum transport phenomena. We can detect it. So that's a time we hit. But then...
You mean like in terms of defects?
They
were kind of teared into pieces?
Because if it is sonicated, it can not only break these materials into single pieces, but it can create some of the defects inside, right?
I see.
So that's...
But you did see graphene, essentially, like a single layer?
No,
like
not the single layer. Using the AFM, we see that it was probably multi-layer, the 5-10 nanometer size of multi-layer. But so if you just try hard, maybe you can just get it, But also my time ran out by then because during my postdoc year, Paul McQueen decided to move from Berkeley to the Cornell. And I decided to stay behind because I had a fellowship at the Berkeley. So basically, I was kind of remain is a kind of small size of the downside his lab with the cryostat without magnets. So I think the more sodium graphene is not possible anymore. And back then I have another project going on measuring the thermal transport in the nanotubes. That worked quite well. And that part I have the good collaborator at the Berkeley. So I focus more of the study onto this nanotube studies. So
how do you do the measurements on those? Like what was the size of those samples of multi-layer graphene? And I know like now we use a lot of like lithography to make the electrodes.
Right.
How did you do the transport measurements?
Right. So the backbone of most of the so-called the mesoscopic study of the quantum materials or the 2D materials, including graphene, and nowadays people are doing. All the technology is already there in the late 1990s, right? So you identify the materials, which is usually size about micron to even just kind of down to 100 nanometers.
What was the size of transistors at the time? Was it already kind of a good measurement?
No, it was well below 100 nanometers.
Yeah.
So so about 100 nanometers, I guess, in 1990s. So and then combined with this the scanning probe, AFM, or the or high resolution SEM, and electron beam lithography, you can wire up any small samples, something like few tens of nanometer to the micron size of sample. So technologies actually developed for the study of the nanotube, just that applicable for the graphene, because size of graphene sample, graphite sample back then is about the microns and 10 microns and that size. So I think in that regard, the time that I spent for the nanotube or time that people spend on nanotube is well spent, because that is technologies now even just being used for the traditional, conventional quantum transport.
So carbon nanotubes, they give you this infrastructure to study.
That's right.
Like putting down the electronic pads or whatever.
That's right.
Lithography.
Electronic pad, lithographys, and e-beam lithography is now being widely used in that way, and how you just kind of wire up the non-semiconducting systems or some unconventional materials in that way, right? So back then also my thermal transport study, which actually I did during my postdoc, that technology required the MEMS technologies. Again, that was a new technology that just comes out from semiconductor, the engineering or the even industry. So that the microelectronic device structures, which is basically not only make the surface device, but suspense structures and the three-dimensional structures, combine that with this nanoscale material, which has been used.
And you were mentioning the Hall effect, that you were interested in that.
Yeah.
When was this already during your postdoc then that you
Yes,
looked into
right.
this?
We talk about the one-dimensional space is a little bit limited, and that's kind of good example. There is once you get to the higher dimension, 2 dimensions, for example, like the graphene, immediately magnetic field do a lot of interesting things, and good example is the Hall effect. So one thing I learned from Paul's group is, okay, so well, you know that with magnetic field a lot of things can be done, although that Christ had with the magnet is taken to the corner eventually, so I couldn't continue, but that was one interesting data mark that I had. Yeah.
Sure, maybe since we touched the base on Hall effect, we would try like maybe explain it on the deadline.
Maybe just like your typical undergrad explanation of the Hall effect, and
sure,
then maybe going to the quantum Hall effect.
Yeah. So that's actually good sidekick topic. So as being at Harvard now, Hall effect has a very special meaning because Hall is named up after the professor Edwin Hall, who discovered this effect. I believe it's 1870s, late 1870s, and it was actually his PhD project. His PhD was in the Johns Hopkins, and can imagine that in the end of the 19th century, the physics in the U.S. is basically somewhere that really peripheral, right? And all the important scientific efforts, including physics, is in Europe. So you can see that this is Johns Hopkins or Harvard. This is relatively new places, and that not a lot of the leading science may go through. But this is one of the exceptions. And Edwin Hall thought, actually, he read Maxwell's paper, and Maxwell wrongly predict that the Lorentz force onto the charge carriers in the conductor may not create this kind of effects because kind of various the discussion he had. And Hall actually challenging that statement, and he wanted to do this experiments for his PhD. And the idea is relatively simple. So if you have the charge carriers, a charged object, under the magnetic field, when charge is moving, there's a Lorentz force, which actually push this charge carrier orthogonal to its magnetic field, and then it's at the velocity, right? So that's kind of something that you can see. So if you have, let's say this is some sheets of the system, and I have the electron, maybe Hall, let's say electron, flow into that direction. This is a kind of if this is going with the velocity v, and if the magnetic field is the getting into the board, now I have to do the direction, right? E and V, so like this, but it's the negative charge. So there's a force kind of pushing this in there, right?
Right-hand rule.
Right-hand rule. Yes, Then eventually that if I want kind of keep the current in that directions, I have to put the charges in here, negative charges there, positive charges there, make the electric field going to the in that direction. Am I correct?
V cross B.
Yes.
V cross B.
Yes. So I think the force is going. Okay. So why this is hard. So important part is, as you see here, that there's always a balancing force kind of build up. In the system once you apply the magnetic field. So when you have the current going through, there is always the electric field, which can be translated into the voltage across the sample. So experiment can be done by sending the current, measure the voltages, and the magnitude of this voltage is proportional to the current, which actually proportional to V, also proportional to the magnetic field. So since current is proportional, the voltage current proportional to the voltage, if we divide by the voltage with the current, and that becomes a unit of the resistance, and this is what one can call the Hall resistance. And Hall resistance, of course, can be tuned by magnetic field, and because of this Lorentz force is all kind of linear relation, resistance is linearly changing with the magnetic field. And that's kind of what Hall Hall discovered. Now, this discovery is not an easy way to do that. Part of the reason is all this physics you can see is kind of already it's a two-dimensional physics, right? So
did you use like electromagnets for controlling the magnetic
now you can think about 19th century. That what do you use?
What do you
right?
have? Yeah.
So maybe electromagnets is there, so that you can have the coils and send the current, but it's not a superconducting magnet, right? Magnetic field you can generate is not necessarily really strong, right?
Yeah, was it like strong enough to kind of?
So how to observe this one? And if you just kind of think about this experiment, there's no semiconductor. Semiconductor is important because I think the magnitude of this, the resistance is inversely proportional to the number of the carriers in here. So if you just try to do with the conductor, it's not an easy experiment to measure. So the key here is you want to have the higher current density into the sample to get the same amount current. To get the higher current density, you have to basically thin down this material, right? So guess what Hall used to do these experiments? What is a 19th century's technology? You can make something very, very thin.
To make something very, very thin.
Yeah.
Okay, I know that.
You know?
I read about it.
Yes.
Cleaving.
Yeah,
I don't know,
not
just
the cleaving.
pushing it into...
People already did in the medieval era. People just try to make
smithing like very thin.
The soft metal.
Yeah. And then
but soft and also
hitting it.
Hitting
very expensive things such that
gold
you want
foil.
gold foil.
Exactly.
Gold foil,
Gold foil. So they call
so
it
use
gold
this
leaf.
for artistic purposes.
Yes. Already medieval times, people know how to make this one. So he used gold foil, which is probably about a micron, even less thick, and demonstrate this, right? So that was kind of a beautiful experiment.
With copper, it wouldn't work? Or copper
it should work. I think after then, basically, he did a lot of the other experiments. But that was his PhD thesis in the Johns Hopkins. And
that's
then,
quite daring also to challenge Maxwell in
that's
in
right.
essence.
Yeah, that's right. But anyway, after this very successful PhD, he basically come to Harvard to be a professor here, and he actually spent probably a good 30 or 40 years at here, and actually build up the kind of important part of the department. And he's been studying a lot of electrical transport into the conductors as well as semiconductor onto the in this lineage. So I think we have some heritage here in America, especially Harvard. So that is a Hall effect and has been widely used for many physicists and even engineers, especially if you are working on semiconductor. That Hall effect is a way that you can get how many carriers in your system.
So for carrier measurements, when was it adopted? Because it seems like there was a long silence from Hall's first experiment to when
to Klaus von Klitzing, MOSFET,
So what was the Hall measurements? Were they used it somehow for
so
solid state?
While this is a kind of a nice demonstration, everything is here is classical, right? I explain everything by the classical physics here, right? So naturally, you can imagine that what is a quantum version of this effect. And already in 1930, early 1930 even, maybe even just kind of even 1929, physicists solved the problem like the Landau. I think also Rabi solved a very similar problem. Solved the problem, say how that charged motions under the magnetic field should be quantized. And there comes that the Landau orbits and then the Landau quantizations and Landau levels, and all this discussion has been known in 1930s. So people know that there's a quantum version of the effect. And once the technology got evolved, then people can make the strong enough magnetic field, a few Tesla-ish, about Tesla, a few Tesla-ish. People did see that there is an oscillation of the resistance under the magnetic field, and known as the Shubnikov oscillation. I think that was probably 30 or 40 already experimentally start to see this effect, which can be explained in terms of this Landau quantizations happening and created this the quantum oscillation into the transport.
So Shubnikov the gas, in principle, they could see this.
Yeah, that's why that name comes from. Yeah. So Shubnikov and the Haas and the Haas Van Arpen and
Yeah.
these people's already, I believe it's 30 or 40s, right? And around the times that some of this quantum effect start to see. While this is quantum effect, that is so-called the semi-classical quantum effect. Part of the reason is that still the electron is behaving in the three-dimensional space. So one direction that perpendicular to the magnetic field is kind of quantized, but along the z direction, it is a kind of free move right along the magnetic field. So all this effect will shows this the quantized orbit effects, but it's still kind of bit of the continuities along the z direction, make this effect kind of still semi-classical, right?
Was this the cyclotron resonance? Or it's a different thing? When they go in the spiral, essentially.
Yes, I think that's you can see that the cyclone resonance is related with the Shubnikov oscillation. So getting to the fully quantum versions, you need two more conditions needed. One, that you need an even stronger magnetic field. That going over all the kind of defects and getting to fully quantum limits and few Landau level limits. And second part is basically you have to really confine the electron in the 2D, right? So that comes in kind of several technological development. The first one is, of course, superconducting wire becomes available and improved. And throughout this, the 60s, 70s, 80s, and people start to make the kind of better and better superconducting magnet. So high magnetic field, something like the say few Tesla, 5 Tesla, and 10 Tesla, and that type of the magnetic field becomes available in some places. Grenoble is a good example. And also their magnet lab in here. In fact, the first magnet lab in US was a Beetle magnet lab, which actually at MIT.
At MIT,
but
opposite of LIGO.
Yeah. Right. So that's a time. But then the next thing is that one has to come up with how to confine the electron into the 2D, right? And that requires technological development. You know that the transistor, the modern transistor work in this, the CMOS, complementary metal oxide transistor, worked onto the gate, the gate oxide and the channel, and within the gate, you can just pull the electron near the surface, and you can confine the electron and the surface. And that's kind of how you can make this MOSFET work it out. But in terms of physics point of view, if you just kind of do it in the right way, this electron tend to be now confined into the near the surface and make the kind of two-dimensional electron gas. And that basically though the directions of the electron is confined enough to effectively freeze out dynamically. In other words, to get into the excitation, you need higher energies. So, the temperatures or the dopings. So once you get to that technologies, then effectively you can make this electron into 2D. And around that time also, the engineers start to develop, in fact, actual physicists, make the semiconductor heterostructures that by just putting the right semiconductor heterostructures, you can also trap the electron at the interface by bandgap engineering. Kind of similar idea. So in the late 70s, in 90s, 80s, this technology becomes available and reasonably high quality electron confined to 2 dimensions start available. And that's where that experimentally the quantum effect was discovered.
So why was it von Klitzing?
Was von Klitzing? Yeah.
He had access to a good MOSFET.
Did he get the good magnet?
And he was working at Grenoble at that time.
So he was working at the Grenoble with high magnetic field. He got the access onto the one of the really high quality MOSFET, and then that worked it out. And it comes as actually a rather interesting surprise because somehow in the retrospect, I think how theorists actually missed out these obvious things, type of things, right? But there's no predictions of this, the whole effect get quantized until experimentally observed, right? And even von Klitzing himself, he see the data and then just look at the Plateau appears and look at the resistance, 25.6 kilo ohms. And then you can see that it's very interesting that he had this lamp note that he published it, or that it was kind of known that there's photographs of the lab note. You can see that it was probably 2 a.m. or somewhere in there, and then he say that with the bottles of the wine,
Yeah, with
they
the
also
wine
doing the
glass.
experiments.
Yes,
Yeah.
yes.
But then you see that this the resistance, whole resistance is 25 or 6 kilo ohm. He's fiddling around that some of this the H and E and C and
And you
kind
could
of
get the number.
E
Get the
scale of
right number.
H becomes now that 20 the right dimensions of the 25 6 kilo ohm, and he got the kind of revelations on that part. And the paper that he just tried to claim that instead of he called this quantum artifact, his paper later published, a few months later published, it is basically finding the experimental way of probing the fine structure constant or something like this, right?
Yeah, I think that's the
Yes.
biggest thing, because
Yeah.
measuring the
Yeah,
fine
Yeah.
structure
yeah.
constant.
So it comes out
at
kind of
high
interesting way.
precision.
So that's a part.
In a dirty material.
Well,
Yeah.
it's not necessarily too dirty.
Yeah, that's dirty, but it's
It's not
Yeah.
graphene.
So-
yes.
It takes about 100 years, indeed. You're right. From holes, the whole measurement in the 1870s, 79, the glitching, the 1980s, it's almost 100
Yes.
years. Yeah.
Yes.
That's the interesting part. Yeah. Yeah. So that's kind of quantum artifact. And you can see that there has been always a bit of the competitions between Europe and US. And back then, the Bell Lab at Grove, people were also working on the very similar things.
Mhm.
And it takes only kind of within 2 years, and then less than 2 years, that Dan Sui and that Holstomer actually using the gallium arsenide,
Mhm.
they see that even the more quantum conditions, they see this fractional quantum effect in the even kind of better sample.
More details.
Did
yeah.
experiment lead there as well, or did theorists quickly catch up once they saw the quantum Hall effect? Did they predict the fractional quantum Hall
Not
effect?
really. Also, that's another interesting part. So the motivation, I think, Horstomer was my colleague that when I worked in that at the Columbia University as a junior faculty. Once I asked that, what motivated you just to study about this fractional quantum effect?
Mm-hmm.
And they were not looking for the fractional quantum effect at all. In fact, the common belief is, well, nuclear one, that is a first lambda, the kind of the zero lambda level quantization. After that, if you just deplete that out, there should be nothing, except that you have the sort of low carrier density Wigner crystal. So they are looking for the Wigner crystallizations.
Oh, right.
And it comes as a bit of a surprise, but that's kind of funny that Kliching's paper talk about the fine structure constant. The Dan Sui and the Stormos paper were talking about the Wigner crystal in the title. Both of them are PRM, but actually no mention about the fractional quantum Hall. So that's interesting.
So was that an
interesting part.
intentional political decision?
No.
Or
I
they
think that,
actually were focusing more on that part?
Yeah,
yes?
that part, and it was a stumble on to the
Yes.
kind of big discoveries, right?
So then who coined the term of the quantum Hall effect?
That's a good point. I don't know. I think there must be some people. Yeah, but that's that was before my time. That when this discovery was done, I was in high school. Well, I was not even high school. I was in elementary school. So yeah.
So when you started at Columbia, what was your research statement? Like, what was your stated plan?
Okay, good, right?
And
yeah.
how much did you do of that?
Oh, that's a good point. Okay, yeah. So when about the time that I finished up my postdoc, so although Paul always is saying that I try to ruin your career by just leaving and desert you in the small lab, I fail. That's what his statement is, jokingly. My research my study onto the thermal transport and nanotube did quite well. So I think we got kind of interesting data. Demonstrating nanotube is a really good thermal conductor. So that was a kind of nice demonstration that will provide me the next steps as a job. So that was good. So when I come up with the research statement, I got the advice from some of my senior colleague that maybe now once you becomes the PI of the lab, you have a little bit more of this the diverse programs you can run. As a junior faculty, you may comes around kind of few project into a research statement. So one that can be done reasonably easily, such that it can provide you some paper. Second, you want kind of also do something harder and maybe quite ambitious. Third one, something a little bit fashionable, but not doing that. So I thought kind of that's the three things, right?
Pie in the sky, impossible.
Yeah, well, yeah. So the first project I had was, of course, I know that thermal transport, how you worked it out, and somewhat related is thermal or thermoelectrical transport, which actually I have a clear idea what to do and how you can just expand that. So that was a project that I proposed, because which will kind of give me some quick turnaround. And second part, challenging. But I have some idea that how I want to kind of push is, well, so I heard from the Paul that, okay, so this graphene can be kind of interesting. I know that although it didn't work it out, maybe there's some way that I can push around. So graphene project is another thing that I put up there. Third one is a little bit of the fashionable pie in the sky, maybe that related with my last project in my PhD time is making these tweezers using the nanotube.
Yes.
So nanotube tweezers. So it's a little bit of the MEMS type of the device or NEMS. Maybe I can just push that things around, or maybe something onto the even bio application or something. But there was a kind of completely kind of not deeply thought out project, but I just put up there. And of course, I didn't push that at all. But anyway, that was my research proposal I prepared.
I'm curious, like nanotubes, were they ever used as like a probe? Because maybe like for AFM,
Yeah.
where you have the needles are, or like the probes are quite big, but for nanotubes,
that's right. I think actually back then the people use a nanotube, attaching the nanotube and the AFM, and that will serve as a really sharp AFM tip, right? So the demonstration we did is a little bit of the expanded that instead of the one nanotube, you have the two nanotube. That all is spaced between the electrode, and applying the electric field between them, you can just kind of manipulating these nanotubes around, right? So that was the idea. But I think the problem to use those kind of system is a reliability, whether you can easily assemble and whether they are reliable enough to just use it. I think that's always hard. So
maybe easy to break those tubes?
Easy to break and easy to detach it, difficult to make, right? Something not necessarily too useful. Yeah.
And then when was the first time you actually got your hands on graphene? So in Andre Geim's Nobel Prize talk, he actually explicitly mentions you and thanks you, and even mentions that he would gladly share the prize with you. When did that collaboration start? When did you start talking graphene?
That is a long talk, but anyway.
Yes,
so
we love it. Give us all the details.
That's also very fun stories there. So when I started out my lab, and we did this kind of few different projects I have in mind, and also Paul moved into the Cornell, and he himself also kind of interested. I mean, this is something that for few people that can be quite interesting field that kind of explore, except that we don't know how to create a good graphene piece, right? So Paul put the students in this project. Scott Bunch, he's a professor in the WU now. Was the beginning graduate students and work on that. A little bit of continuing of the approaches I started out in his lab. So Paul and I always kind of communicate. All right, so that Paul think that, well, you know that I'm happy just so you kind of explore this thing. But it was a kind of friendly competition in some sense. We want kind of inform each other how things goes. I think it was very nice of him, by the way, just suggesting that. So I thought I want to approach it somewhat different directions. So while that I was kind of reading through when Paul suggests that why don't you do come up with the idea, the making graphene, I went through some of the few literatures back then, and there are some people actually did interesting approaches. And if you just kind of look through the paper, one important paper that I found is the it's a very obscure journal, was written in Japanese, in the Japanese journal of the Tanshu or something like this. It's the meaning of the carbon in Japanese. This is Professor Haas in I think it's a Keiko University, or I forgot the exact. That she actually did break these graphite powders into very small pieces. And she managed to just kind of demonstrate that one can make the device out of it. I don't know how she did it, but anyway, there was papers, a kind of report that can do that. Right, that is one part. The other one around that time that Rodolph, who is now in the Unistan Korea, well, back then he was in the Texas, Austin. He actually showed that, I don't know why he did that. It was around kind of mid-90s. He take this HOPG, the highly oriented graphite, pyrolytic graphite, which has been used for the STM people that imaging the graphite surface well. He basically patterned this, the HOPG using the micro patterning and make these pillars of the HOPGs, right? And then cleverly, he just grabbed that, put onto the silicon wafer and just kind of put on there and demonstrate. And very nice image of this cleaved crystals. It was a reasonably thick, but you can imagine, right? And the thick cleaved crystals and take the photographs and report that into some of the journal. And this is kind of rather inspiring. So I just kind of remember that, wow, okay. So I know that when we just do the sonication, you can break the crystals and take the defects. So I didn't tell Paul that, that is not a kind of really promising.
Something gentle.
Yeah. So I know there's something gentle. So I decide, all right, maybe those kind of between OHASH and then the Rodolph's method, there may be a way that we can think about. So so the way that I just thought is that maybe using this the AFM, but instead of AFM tip, going back to the nanotube on top of the AFM, right? Instead of doing that, what if I just make the graphite blocks as AFM tip and then bring down AFM tip onto substrate, which actually I can control the normal force, which will control the frictions, and try to cleave it off more controllable way. So idea is basically, well, you just prepare the pencil for me, right?
Yes.
Yeah.
Same way that if you have to grab the pencil, write on the paper, you make this lead, this type of the pencil trace. If you just take a look at this pencil trace with a microscope, I'm sure that you will find out the pieces of the graphite, the detached from the pencil lead, right? So let's do this one much more controllable way, such that I can make
You
it.
can even actually look at maybe under the microscope.
I don't think that you can see that.
I don't think we can see much. There will be a little bit of structure, mostly from the paper.
Okay. Yeah. There actually, if you just Google the internet, you will find out the better the
Images,
SCM pictures. People did that, but try out. Yeah.
We can go downstairs and take SCM pictures later.
Or I can just lend you that better optical microscope with highest resolutions. Yeah. While you're just doing that.
Yeah, but that is just the paper structure.
It's paper structure.
Yes.
Yeah. Right. So the task we had was that, all right, the making the AFM tip, the made of the graphite blocks. And so I had my first generation students, and among the first generation students, the Yambo Zhang, who is now a professor in the Fudan University. He's a very creative guy, and he's very motivated onto the potential project I described. So he started work on that idea, and then out of probably his very hard work, about year and a half of the hard work, he started kind of produce this the nano pencil, basically AFM tip made of the graphite block, and then with a little bit of efforts, he started kind of cleave that rather thin crystals onto the silicon oxide substrate, silicon wafer. And you see that once that your sample is separated out in silicon wafer, you can make the device, because that's kind of the way that we make the device on nanotube, right?
Yes.
So from there on, that we know what is the technologies there. So so we made that the device. And because this one is not sonicated, and you're starting from the high quality of the graphites rather than graphite powder, in some sense, the quality of sample is good enough. So once you just do the transport measurement, you can start to see that strong gate dependence, very strong Shubnikov oscillation, semi-classical the quantum oscillation, which actually tuned by the gate voltage. All these things is a kind of very exciting result that start comes around.
So can you do the quantum Hall effect measurements?
Not yet. So Shubnikov oscillation is a precursor of the quantum Hall, right? So to get into quantum Hall, that you have to get to the really long the period of Shubnikov das. In other words, you have to populate only a few Landau level, and that's only where you get the reliable quantum Hall, right? So still we have some way to go. Part of the reason is it's not a graphene, it's a graphite. The thinnest crystal we could get is probably 3 to 5 nanometer-ish, which means probably something like the range of the 10 layer, right?
The other thing I noticed about the fractional quantum Hall effect measurements, they only observed it at very low temperature. So once it's like 1.5 Kelvin, they couldn't see the trace. But once they move to something like a fraction of a Kelvin,
it also depends on the disorder in the sample.
I see.
Right,
So
and then know that this one is old, maybe 20 some years, 25 years old, 20 years ago. So quality of sample is very different back then, right? So Jambo made this thin enough sample, but not a single layer. But we thought it was very close. Part of the reason is that, I think it was not fully optimized yet. But starting from millimeter thick samples, now you have only a few nanometer. So many of those magnitude went down.
That's an extremely difficult exeriment, like modifying your own AFM to make these tips. It sounds pretty tough.
It's doable. It's tough, but it was doable. Yeah.
How do you measure the thickness of?
Okay, so that's another part. So you're using the AFM again. That other AFM that measures the thicknesses, and then that's yet another things later. Back then we just didn't notice that, but I think that can potentially have problems because the Van der Waals force on top of silicon oxide and on the top of the graphite can be different. And
so it pushes the tip.
Yes, apparent thickness could be different, depends on the set point, right? But if you use a kind of not a tapping mode, but a contact mode, you get the decent sense that what they look like. Anyway, so we felt like, I think we start getting the really good regime. So this is a good time we can just report both making the AFM tip and then making this transport. So
did you try to use like optical, was it known the absorption percentage?
We'll go there. You
mean the transmission measurements?
Transmission measurements.
Yeah, transmittance,
So we are anyway happy to see that the quantum oscillation. So that was 2004, around the summertime, and there was time that I started my lab about two and a half years ago. So after 2 years of the hard work of Jambo, we went to this result. We started to write it. And some of my colleagues know that my close colleague that knows that I'm just kind of working on this type of the project. So I cannot name the colleague because it's a broadcast.
How secret do you need to keep your project?
No. I think my colleague at Columbia knows about these things, right?
Yes.
But this particular colleague, that one kind of close to the end of the summers, I think I was kind of writing the paper, came to my office and told me that, hey, Philip, I thought you are one of the crazy guys and tried to make the graphene, but guess what? I'm just reviewing a paper. But there are even crazier guys out there.
Oh, this is where the story
So I told my colleague that I'm writing this paper, so I want to kind of know about the papers. I don't want to be interfered
Yes.
because I want to kind of finish up this paper. I'm very close to kind of finish
Yes.
up paper. So let me just write and submit the paper and just ask you what it's about. So I wrote the paper quickly and submitted. I think that's the end of the summer. And I kind of get to my colleague and then, hey, now I submit the paper. What's about it? And he told me that these names, the Andrei Guy and Kostya Novoselov. I think that's the first time I heard about it. But he briefly mentioned what is going on. So I couldn't believe that kind of how that worked out. But in fact, that paper was posted in archive.
Oh,
it was, I
yeah,
see.
yeah.
No,
so-
actually,
yeah.
around the time or
Yeah.
something like so soon that I knew that what it's about.
Yes.
And reading this paper in the archive was amazing. Amazing in a sense that you got shocked. Part of the reason is, first of all, that we found that our data is exactly a subset of their data. So very similar data because they did make this the thin sample of the graphite and do the transport measurement, magnetotransport, gate dependence, Shubnikov Darcy effect, gate dependence, and things. It's a subset in a sense that they also claim that they can get down to the monolayer, right? And indeed, their transport data is showing not the monolayer in that paper, but very thinner layer.
So
Right.
they didn't show in that paper originally that they can do a single.
I believe that in that paper they didn't get yet to the monolayer transport data. I
see.
don't know what, exactly, but anyway, so it was clear that was a paper. So I felt like I think that paper was the reviewed in Science already. My colleague to submit this favorable. Of course, it's a good paper, right? So I knew that we were completely scooped. I think both the timing as well as the contents, I think, but the other part really surprised is how they can get to this thin layer, right?
Did they have a method section? They had a method
They
section.
have the
with
detailed method sections,
Yes.
and I couldn't believe that because that's another shock because they use the adhesive tape.
This is exactly this
Did you
one.
immediately try it out? Did you immediately try doing that?
So when I just look at them, when I hear about that, first of all, that okay, it's complete scooped, right? Feeling of the complete scoop. Second, that I was only the 2.5 years into my assistant professorships. I start worry about how's my tenure case work, right? Type of thing. But then I quickly realized that I missed my key in my porch type of the feeling. Because when I read, when Paul McCann asked me just making graphene, I searched through the literature and I mentioned the Luof's work and Oash's work, but there's a work that I didn't mention, even Prio work to you guys. There's a person's name's Flint, Robert Flint. He was the professor on Simon Fraser University in Canada. He made the earliest paper he made on this direction is around the 60-something, and he's the one that preparing the TM sample using the transition metal dichalcogenide. And he started with the chemical exfoliation, which is basically sonications in the solution, right? And he actually, it was in the Cambridge, but then he moved to the Simon Fraser University, and he actually continued that work in various different way. But then there was a paper in 1972, I believe, published in PRL, sole author paper, only one person. Simon Fraser University is a relatively small university, and the experimentalist published a sole author paper is really rare. But what he did was another TMD, in this case, niobium diselenide superconducting TMD. He reported that atomically thin TMD, that TC got changes. That's a kind of report. And it was that scientifically, it start kind of really makes sense because, as you go to low dimension, there's more of the fluctuations and TC tend to be dropped because of these fluctuations. And then you naturally think that how he made that sample, right? Guess what? He used a Scotch tape.
Really?
Yeah.
So I read that paper. All this
When was this paper published? Which year?
1972.
1972. Wow. That was like,
PRL.
Wow.
so people kind of overlooked the Scotch method.
So I read the paper. When Paul actually asked us to look through the,
Oh, so you immediately made the connection. You were
I
like,
made the connection. So that's why I left my key in the porch. Right?
Yeah, because someone had already given you the key.
So that was, but I remember that why I actually dismissed that, right? I thought, wow, result is really great. But wow, using the Scotch tape for the serious experiments, right?
Too simple.
I thought kind of PRL. Back then, PRL is really no one want kind of publish it into the Science and Nature than PRL. So wow, the PRL is a serious paper, the serious journal. How come that this paper using Scotch tape make through? That was my fear. So I just dismissed it, and that was my mistake.
Do you know if Andre Geim knew about this paper or he just rediscovered
I think that
the method?
later, I don't think that he knew about these things, but I think he later write the review, and of course the Flint work is in there, so it's in there.
But he came up independently with the Scotch tape because he was doing the Tuesday evening or I don't know, Friday evening. Friday evening.
They tried to clean up the graphite, the expensive graphite.
Yes.
And then some student he used Scotch. And then they found in a trash bin or something like that. I don't know. Maybe you can explain.
No, I think there are various versions. You have to interview the Andre. You have to compare the note. Right.
The lab notes.
Yeah, but there's an important part, and the important. I think, of course, I think this is a really clever idea that just using a rather simple way, but also all of these things, we immediately switch it. Of course, Yambo was really somebody really disappointed by complete scooped, right? But Yambo is also kind of quite encouraged, that whatever method, if you just kind of get to the thin sample, one can get it, right?
Yes.
So he just abandoned almost immediately, even just 2.5 years efforts, get the Scotch tapes and just try it out.
Damn.
Within a week, basically, that we start to get almost reproduce what they are getting. So I think that was kind of the interesting part of the story. We immediately understood the advantage of the Scotch tape. Part of the reason is that that this nano pencil method, you can cleave it, and potentially if you just control this the adhesion force well, I'm sure that eventually you can optimize this one, can create something very thin. Problem is that this is a really serial method, right? But imagine that you have the Scotch tape with the graphite crystals and cleave it off and Scotch tape it and rub it out. There are billions of nano pencil working in parallel, right? So that cleaving efficiency is extremely high, right? The only downside is there are a lot of junk, right? A lot of thick crystals. How to find the thin crystal? That's basically important part, right? There, I think there's also lock factors in there, right? So the way of this Scotch tape method is basically it can be extremely efficient parallel way of the producing the sample if you can identify the thicknesses. Now, using the AFM, you're going back to the serial method and getting this monolayer or thin layer is probably, it's also not necessarily better than nano pencil, I would say. So what is a way that you can identify the thicknesses? Because it's optical contrast, right? But how do you get the optical contrast? I've been seeing that this thin crystal onto the silicon oxide, silicon wafers, right? Even back to the Berkeley time, right? But there is no way, that easy way that you can just see that thicknesses. They all graphite look similar, right? It's not necessarily thin crystal is visible there, right? the key there is you have to tune your oxide in the right way to keep up with this our sensitivity of the eyes to get the really identified contrast. And there's a if you later there is even paper, I think Gimes Group's paper as well. Compute that. This is a simple calculation, right? What is the dielectric constant? The thickness is right. If you just kind of do the number right, 290 nanometer of the oxide is one. Maybe slightly better if you go to 90 nanometer. But it was a reasonably sharply tuned. Within kind of 5 to 10% of that thicknesses, you get the good enough the optical contrast. You can identify the single layers, right? I don't think that you have to interview the Andrea and just check the note. I don't think they initially used that the wafer with some careful tuning, but potentially it was a kind of some sort of luck. Somehow that right size of the oxide is in there.
Yes.
So was it a standard like silicon on silicon?
Now it's standard. Now it's a standard because everybody working on the 2D materials.
Yes.
That is the number.
No, from like microfabs for
can be any numbers. It can be any numbers, right? I would say that for the nanotube people, it's about the micron is better because you want to have you don't want kind of punch through the oxide, right?
Yes.
Yeah.
So it's between always Paul and me that jokingly again that blame each other. Paul always said I hired the wrong postdoc to I missed the Nobel Prize, and then I asked Paul that hey, if you just don't desert me into the Berkeley lab, story could be different. But then we all agree that no, we couldn't make it because we are not lucky enough that you have this 280 nanometer of the oxide.
Could you show us how would you do it with like is there
have you tried
what are the
it like have
ingredients?
you tried it I suppose you've tried it as well.
I think you know that when I just kind of prepare that bring some of these things my students laugh outside that they're saying that I want to see how the Philip prepared the sample.
Can we get one of your students to prepare one?
I think I can. It will take some time because you need the right thickness of wafer and right prepared.
Right, to be able to see it afterwards. Yeah.
You know that I can show you that.
And there's also always urban legends that this only works well with Scotch tape and not other brands.
No, I think later if you see my lab, I think there are a few different versions that you will see that. Yeah, right. So you can see that this is a slide that shows how to prepare the sample. You start from the graphite. You have the Scotch tapes, right? You crush this graphite into the Scotch tapes, look like this, right? And then put the Scotch tape onto the silicon chip, and you have to rub it.
Oh, rub it. So it's not like multiple times is.
Oh, you can just fold it multiple times and then clip it off.
Everyone has its own recipe.
It's all kind of black art, you can imagine, right?
Yes.
And then you can rub it by finger. Some people like to rub it with these the tweezers and then erasers.
Cool
I've done it
one
with
of your students could show.
I've done it with HBN before because we did
you
some
can just
HB.
demonstrate. It's the same thing. It's the same thing. Yeah, same
Well,
thing.
it's like it's like you need to do the right
Gently,
pressure.
yes.
By the way,
it's like
there's a video.
skill.
There's a video clips in YouTube. I remember it was already many years ago. There, I think the one of the best video clip I saw that probably you can see in the YouTube series. The Barbaros Oezemas, one of my first postdocs. Now he's a big professor in Singapore. Back then, many years ago, his students made this videotapes and put into the YouTube. So anyway, so that's kind of all possible. Okay, so that's basically the time that we got scooped, but we just copied and we start to get the result. And another funny story that we had was that so that was a kind of 2004, and Andre and then Kostya, the paper was published in this Nobel Prize winning paper was published in 2000, same year, I believe October-ish. So that's about the time that the paper was published. Our paper that we submitted over the summer, that for APL and PRL both get into the big trouble because you see that people reviewers saying that, hey, look at these papers in archive. I think they did better than you guys.
Well, did better, but still, I feel like it's
It was
complementary.
Well,
based on
officially
different
published at that
methods.
point.
I have to argue that, yes, well, look at the submission date and why, that it was before that. It should be
do you regret that you wouldn't put it on archive? Or?
No, we put in the archive.
Oh, you put archive.
Yeah.
Archive. I believe that we put in the archive as well, right? But anyway, so it was later than the submission days or whatever things. So anyway, we argued that, and eventually after a couple of the round, that kind of went through that. But nevertheless, I think that's a part. Now, interesting story is that the March meeting in 2005. So after Geim's paper, it was not immediately acclaimed that, wow, that is a breakthrough. I think it was kind of interesting paper that people just kind of looked through, but was not necessarily acclaimed. So Geim is not getting, I don't think that he got the invited talk in 2005, right? But anyway, there is a very obscure sessions in the APS March meeting that Geim's papers and that Geim's talk and my talk and Walter De Heer's talk was put together in one sessions. And I knew about Walt, who actually tried to grow the graphene with the CVD method, because he was a former nanotube the researchers. So I know. But I never met Geim because we have been in the different communities. I've been into more of the nanotube. Andre is more like the 2DEC or more mesoscopic type of the community, was a little bit kind of different community. Somebody, I think later there was Doug Nettles and the Rice University confessed that, one thing that I contribute to graphene research is in the Soros meeting of the APS March meeting in 2004, I found that this to be interesting, the talk, submitting the different category. I just kind of put them together into one session.
So they could talk to each other.
Yeah. So that's the time that I first met Andre. And then, and of course, Andre is a much more established person. I was just merely assistant professor. So I just kind of again, I approached Andre, hey, good to meet you. Finally, I meet you in person. And you know, by the way, you scoop us completely. And Andre actually knew about my paper, which is posted. So I think that he was kind enough that, it was a good work. And then, but actually, he made a really good suggestion. Actually, I'm really grateful because he said, I think if the next time that this thing's around, because now we know each other, I think, well, let's have some kind of discussion such that if it is really close by, we can just do the coordination in submissions. So that's kind of the suggestion he made, which actually is kind of very nice of him.
Yes.
Right. So that's kind of my first encounter with Andre. But then coordination came much earlier than we thought.
Is this the one? Or
Yes.
the 2025 nation?
Yeah. So that's within after March meeting that we all went back and Yambo start kind of make the already he started to get the really thin limits, thin monolayer limits, and the quantum transport shows indeed really quantum limits and get this the first observation of integer quantum Hall effect. And that's at the time. That paper is back to back with the Geim's group.
Yeah. I've seen it on the Wikipedia. At the beginning, I was like, ooh, was the Nobel Prize paper was 2005? Or?
No, it was 2004 because I think
earlier,
it's
yes.
clear
It was
that
like back-to-back, basically.
Yeah. So that's a time that the coordination. In fact, turns out in the beginning, especially, there are a lot of papers actually back to back. Part of the reason is, in some sense, it's kind of clear that what is the next moving targets, right?
Yes.
So the often that it is, I would say, the kind of rather friendly competitions, and then many papers came as a back to back, and sometimes the coordinations, And sometimes you even just write the paper together.
Is it also
Right.
easier to publish in like nature journals when you have two papers which are strong?
In some sense, yes. Because that naturally gives that credibility of the work, right? And so often that now, even nowadays, not only my group, many people, especially so-called hot field, you can see that many paper comes at the back-to-back, and even just most extreme case, I see that 4 or 5 papers in the same
The
subject.
whole session
Yeah,
of the nature.
yeah. So there was that sometimes it do happen. Yeah, right. It's a rare, but yeah, 2 paper back to back is quite often. Yeah.
Is this the most
Or the room temperature?
cited?
That's the first of integer in quantum Hall effect is a paper probably cited most among my papers. Indeed, the most cited paper. Well, it's now kind of rather histories, and then room temperature. The quantum Hall effect is basically it is the collaboration with the Grimes group. Basically, Kostya Novoselov is the first author, and then
It was the room temperature quantum Hall.
Yeah.
yes, it was kind of 2 years after this paper.
Wow.
And, that was an interesting work because
that's a big move. Because before quantum Hall effects were only at the
only at the kind of
cryogenic
cryogenic temperature. Yeah, that's right.
Yeah.
It's a brevia, science brevia.
Yeah. But that's the story behind of that is, of course, as you can imagine, that in terms of the sexy story you want to make is something. Well, now quantum Hall is not only low temperature physics; it can be done in high temperature. There is some caveats there, right? High temperature is possible because you see the magnetic field there is 45 Tesla, 30 some Tesla, right?
Where did you do the measurement?
So that is done the high field lab in the Florida, as well as the European magnet lab, the Nijmegen.
Yes.
Right. So interesting politics in there is, of course.
Wait, I want to share that.
Interesting politics is there that, of course, once the quantum Hall is there, and the immediate thing that you notice in graphene quantum Hall is different from gallium arsenide because it's a linear dispersion relation. Therefore, the Landau level separation is not uniform, unlike the gallium arsenide. So that's kind of one difference. And especially the first Landau level is really well separated out. So that energy gap is, if you convert in terms of temperature, 1,000 Kelvin. Right. And it depends on the, if you have, say, 20 Tesla, 30 Tesla of the magnetic field, is 1,000 Kelvin of this separation. So it is really well separated out. Of course, gap size is not only important part, but also you need a lower disorder. So you need kind of something. So you need kind of eventually go to high enough magnetic field to see this one in higher temperature, right? So that was immediate, right? Is there scientific values in there? Well, it's a good demonstration, not much scientific the scientific value. I'm the phototheorist. Room temperature is yet another temperature, right? It's not
but for the experimentalist,
but you can just imagine that just kind of public announcement. Finally, that quantum Hall effect is being seen the room temperature, right?
Yes.
It almost sounds like finally we have the room temperature superconductors. If you just say that, they can be done on the 300
pressure,
300 gigapascal, right? Very similar type, but it was a really part. So especially the magnet lab, which actually is a big entities, right? This is really good for them.
Yes.
Right.
Yes.
What you can demonstrate why the magnet lab is important, right? We can just kind of create the room temperature superconductor, room temperature the quantum Hall.
Yes.
So both European magnet lab and Florida magnet lab is strongly support this one.
That's great.
Right.
Yes.
And that's why that when it comes with this paper, it is a very short paper because it was not much things that we can report in terms of science, except that nice demonstration, right? And it was coordinated between the European magnet lab and US magnet lab, and then want to say that, well, we are important type.
So you just sent the samples around and they did the measurement, or did you send a student
I
with
think,
them to do everything?
we did each other. And there was a competition, but the turns around, we are doing the same thing. We better actually just can put them together.
Yes, yes.
So for magnets, I mean, it sounds quite insane, like in terms of 40 Tesla you said. So what's the records for today's magnets? I mean, probably
So-
like in
Like
fusion.
fusion, yeah.
Yeah. And the fusion is a little bit different stories. And then I think for the fusion, I think superconducting magnet is probably more important for them. And the highest magnetic field for the fusion magnet is probably, I don't know, I'm not an expert on there. But the magnet lab, the record is setting by the hybrid magnets, which means it outside is a superconducting magnet core, but inside is a conventional electromagnet, such that there is no critical field that you have to deal with in superconductors. In that hybrid magnet, one can reach about 45 Tesla. That is still the highest record holder in the it's in the Florida Magnet Lab. Europe's, I think they don't have the hybrid as far as I know. So something like the 30-some Tesla is the highest record. If you pulse the magnet, you can go even higher.
Yes.
So if you go to pulse the magnet, I think record is something like 80 Tesla-ish. Yeah.
Yeah, makes sense. Yeah.
I feel like on this quantum Hall effect, one of the outcomes is that you demonstrated this 1/2 fractional
Yes.
performance. Like,
Yeah.
Did you expect? Were you aiming at to observing this 1/2, or it turned out to be?
When I
an
see that,
experiment?
no. I think that's a kind of another part. Although I would say that some theorists, they vaguely predict in the one way or the other those kind of half integer shift of the the sequences. So first thing that really strike us is that the quantum Hall effect is seen in this graphene, but their sequences, singular graphene, goes something like the 2, 4, 6, 10, and some interesting sequences. And you have to just understand that where the sequence comes from. And it seems like half integer shifted the quantum Hall, and that's kind of important part. Later, it is related with this the Betty phase that associated with the Dirac spectrum. So in some sense, a really important part here is not only observation of quantum Hall, but this sequence tells you that indeed this is a Dirac spectrum with this unusual Betty phase associated with that. That is a kind of the first clear experimental observation, and that's kind of what's exciting part. Theory, I'm the ones that it has been seen that kind of quickly that theoretical explanation comes through there. And if you just digging out the literature, I think there are some theoretical the predictions predated for the experiments, but it has not been widely known. So at least for me, I'm not sure that Andre, but this half integer shifted quantum Hall is not something that I expect to see in the beginning, right? Yeah. So that comes as a bit of the surprise.
I feel like in general, I have a question like for Hall effect measurements. So it seems like this integers, for example, for integer quantum Hall effect, sometimes it's they don't follow like 1, 2, 3, 4, 5, 6. Some of them skip.
Right.
So what happens?
Right.
Why some of this? I guess it's also Landau levels. We can talk about them.
Yeah.
Why some of the levels are kind of skipped?
Yes. Yeah. So let's say that if I have just a Calder arsenide with the regular parabolic spectrums, and then usually quantum Hall effect appears like the 2, 4, 6, 8, and kind of even integers, right? In small magnetic field. If you apply the strong enough magnetic field, each of the Landau level spin degeneracy start kind of breaking out, and then you see the every integers.
I see.
Right. So that's kind of So degeneracy broken to give you the integers. What you are seeing here is basically it goes like the integer 4 increases, like the 2, and the next comes as 6 and 10, right? So which means that each of the Landau level is degenerated with a 4. And that degeneracy 4 is a related spins, and there's a 2 valley. In other words, I have the 2 Dirac dispersions into the graphene band structures, and that comes as a 4, right? But then interesting part is basically I can see that Landau level start to increase to 4, but why actually starting from not 4, but starting from the 2? So that's kind of important part. It was increasing with the 4, but half into shifted, and that is related with this the battery phase related spin half spinners there. Now I think in the retrospect, right? If the quality of the graphene sample is good, then even very low magnetic field, you start to see that all the degeneracy is lifted, and then you will see that quantum effect in graphene like the 1, 2, 3, 4, which is kind of not too distinguishable with the gallium arsenide in some sense. Was less exciting in that way, right?
So,
And in some sense, somehow nature naturally guide us because our sample quality is not good enough, right? We don't see the breaking, symmetry breaking. So just looking at this data, we could already figure out many things about many things related with this battery phase. Same story, I can say that highest quality of gallium arsenide applied the magnetic field, you see the quantum Hall effect, but it's not going something like your quantum Hall sequences, let's say with R, with the P, X, Y. You see that quantum Hall effect shows something like this, like this, right? So it's 1, 2, 3, 4, it's something like this, right? But highest quality of gallium arsenide is not like this.
I see this.
There are many steps. It's all the fractions start to show results, right? And that's if it's better sample, the more, right? Imagine that you measure some sample like this. It's very difficult to figure out what is really going on.
Yes.
Somehow nature is kind of, such that it just start to give us something that we can digest. That's that's interesting, right? Because we start with the integer quantum Hall, which actually can be figured out. And then fraction comes in that's the one. And then you start to see what is the frame there, you can see that.
Yeah.
A very similar story goes with the graphene.
Yes, much easier to recognize the integer version of that when you see it, yes.
I don't know, we are lucky.
Yes.
I think there is another cool thing in condensed matter physics, which you mentioned already several times, like battery phase.
Yeah.
If we can give a little bit of intro into that observation.
So the easiest way that we can understand the battery phase in terms of quantum mechanics is just look and spin half. So one thing that if you read this, when I was reading when I was young, that Stephen Hawking's history of the time, arrow of the time. What is it?
A brief history of time. Yes,
was a completely ununderstandable. But one thing that I remember that while reading is he was explaining about the spin half. And using this the spade card and just rotate it, and basically half of the rotation is related. I think basically twice of the rotation is related with one full rotation type of the idea.
Oh, like this
one. When you can do with the cup dance, right?
Right.
I think that's what I was explaining.
You can do it with the cup dance. Yeah.
So that's precisely one of the best way of the interpreting battery phase. So it's equivalent only when you just turn around twice that 1 turns. What does it mean is if you just kind of make the 1 turns around 360-degree turn of the spin, it doesn't go itself, right? But we know that from quantum mechanics, what happens is your wave functions get a sign, sign changes, a negative sign, such that you turn twice, then basically -1 squared becomes just kind of itself, right?
Getting a pi phase.
Right, pi phase. So that's kind of good way of getting the pi phase.
Yes.
So in some sense, in the electron in the graphene, where that according to the Dirac dispersion relations, if you make the 1 cyclone orbits, it's not considered as a kind of full 2 pi turn. It is only kind of pi turns, right? So if you just kind of apply that idea, basically, that integer sequences actually shifted because of pi turn, because it's only half turns you turn around. So if you just use that languages, naturally that this comes as experimental observer. That is kind of very cool things indeed, right? So unusual, the observation of the pi phase shift into this quantum system. I think that's kind of the part. it turns out also this is although graphene itself is not a topological material per se, this kind of give you the appreciations that how this Berry phase and how Dirac spinors that tied these topological structures can be appreciated. So if you look at the very first paper that how the topological physics comes around, it depends on the people that how you just kind of turn around. But when Charles Kane and Gene Mills they wrote this very important paper about the quantum spinor effect. In fact, that is they use graphene as a starting point and throw the spinor coupling there to just kind of demonstrate it indeed in those kind of system that this Berry phase coupled with the spinor coupling can play the important role and create a new type of the topologies. So that's good part. And going back, even Haldane's model in the 1988, another Nobel Prize winning paper, he precisely deal with the graphene band structures with the additional that the complex second order the tunneling coupling constant, which can be actually viewed as the interesting way of applying the staggered magnetic field in the graphene. So that's why you can see that this experimental observation of the pi phase shift is in some sense kind of interesting experimental incarnations that how that what theories before and after that try to make the topologies bring into the condensed matter system.
How does the pi phase shift manifest itself in the measurement? Like, where do you see?
So there are a few things, and in some sense, the sequences of the quantum sequences have integer shifted. Same way that in fact that is related to this paper. If you go to the Shubnikov Haas oscillation, which is a precursor of the quantum Hall effect. If you look at how the Shubnikov Haas oscillation phase got changes, and the phase is one way directly measure, so the Berry phase associated with this quantized cyclone orbits. Yeah.
This also opens path towards like the anyons, right? Since electrons has the pi shift when you do the full.
It's probably related.
Like
it's related with these anyons eventually. But at this point, yes, indeed, the any of this quasi-particle, when you just exchange your braiding, they have their own kind of phase comes around, especially in the many-body quasi-particle. This phase shift is a kind of important part in that regard that can you actually detect this phase shift is related, but not directly related with these experiments.
To what extent did you have collaborations or particle physicists starting to knock on your door? Because this is kind of a neat system to test some math that
until today, it is me that who usually knock the particle physicists doors to learn about these things rather than the other way around. Our particle physics colleague is so lofty, so they don't care too much about what is going on.
Because I feel like sometimes you have client tunneling or whatever, where you're like, oh, I know the math. Let's maybe like see how it works in the Dirac system.
That's right. But it is true that when we wrote this paper and started to learn these things, I thought I learned some of the field theories and those kind of things during my kind of educations, the undergraduate, graduate educations. But I always felt like, that I'm going to do condensed matter experiments. Think that all this, the field theories, especially now, if you start with the Lorentz groups and then the Lorentz invariant description of field, I thought it was, that electrons moving fast in the condensed matter is only 1% of speed of light. I don't think this is necessary. But at least I heard about this Dirac formulation, all of these things. I was kind of quite interesting and intrigued that all these things that I thought I just learned this one as general educations, but not too relevant, comes back to my life and becomes kind of quite important. And same way that many analogies that are being made onto some of the higher energy physical concept. Klein tunneling is a kind of one part. Another like the Schrödinger criticalities and all of these things start realizing this graphene or the low dimensional system. It's kind of quite interesting. And indeed, a lot of the physics that high energy, low energies and kind of various fields can be connected. And this is one thing quite kind of interesting to learn that how these are kind of connected and one can affect each other. Yeah.
And is graphene, is it like special in a sense material for this Dirac cones? Do we know other?
Well, nowadays, I
materials?
think after graphene, there are more of this, the many topological system where the Dirac dispersion becomes quite important, right? And also borrow that some of the high energy physical idea, like the Y semi-matter is a good example, right? And that you can explain it in terms of the magnetic monopoles and two wire point is connected each other, like the Dirac string, a lot of things that you can just borrow this high energy idea. So there are more and more examples that actually comes around, right?
Yeah, and then after graphene, there's also been an explosion in Van der Waals materials.
That's right.
How do you go about picking what material to work on? Like,
Yeah,
what guides your interest?
That's also kind of interesting, the part. I think, so graphene research started at 2005 or 6 and becomes kind of rather explosively kind of expanded out. I feel like I have been lucky because although we got scooped, but we are close enough in the front line. So we quickly lied onto this wavefront. Just basically, I feel like wow, no, this is kind of really good sailing and push it behind the wave and kind of really exciting times. The graphene discovery of the graphene, the Gaim and Novoselov got recognized by they got award the Nobel Prize in 2010. Some people thought that might be just kind of getting into their peak time and maybe that like that nanotube, which actually is quite exciting, interesting, but maybe phase spaces got all occupied. Maybe what is the next directions to go? It's everybody was a little bit kind of thinking about that, and the different directions here is of course many people that start to realize that this 2D material is a kind of interesting directions to push anyway. It's like the graphene like so. It was another one initiator. I think that there was many people who naturally think that next direction is going further some of the different 2D materials with various different kind. So there are a few review papers and few kind of prospect papers in there, Gaim included. So it was natural directions to push. And especially once that you start to include the semiconductor and superconductor per se, I think.
Cuprates as well? Because this also have some lead structure. I'm not sure how.
That's right. Cuprate included. But cuprate has a little bit of difficulties. It's not easy to separate the one single monolayer, not degraded. So it required a bit of the careful the control. And the few group actually managed to this careful control and showing that cuprate can be also manipulated and studied in that way. But it took some times in there. Yeah. So that was natural directions. And around 2010 to 12, I think that a lot of efforts start kind of pushing to this wide range of 2D materials. Yeah. And there, the 2D material per se is one way, but important ingredient there comes from that making heterostructures out of it. And that has kind of its own kind of interesting value. So I think that's kind of where that I can also mention that the important the collaborations I went through, I enjoyed at Columbia University. So I started at the assistant professor at Columbia, and when it started out, Columbia University used to be very dominated by the high energy physics. There's only very small condensed matter physics they're working, the physicists are working there. And Columbia actually expanded their condensed matter physics efforts in late 90s by recruiting that a few very prominent condensed matter physicists, including Horst Sommer, that I mentioned about the fractional quantum Hall effect that discovered, right? So, and when Columbia recruited him, within 6 months he got the Nobel Prize. So it was
a good hire.
Good timing, right? So Horst Sommer, Aaron Pinchuk, Tony Hines, and these people are moving from the Bell Lab and IBM Lab to the Columbia and really make the core of this Columbia efforts. And with existing the researchers, physicists, and chemists at Columbia, they make the NSF-funded nano center. So really particularly geared toward this low-dimensional electron system. So I was one of their junior hire, and so it was kind of very collaborative environment, and you see that it was like the many good parents and a few children. So you can see that the mentorship that I received was amazing. Was the amazing mentorships and very collaborative. It's something like that they try to implement that the idea that worked in the Bell Lab and IBM Lab in more of the collaborative environments. So including senior and many juniors that kind of joining there, that kind of quickly build up the very collaborative the research environment, which actually has been quite important part of throughout the research. So one of these important work is done around the 2010 to the 11, 12 and that time, 2010. So we know that 2D material in general can be quite useful, right? But then you can study like the graphene, like the one materials that kind of separated. But is there a way that we can actually combine them together? So there's a kind of group of students and postdocs that belong to the many groups. It was actually more grassroots idea that they came up with the idea. I think the Andrea Young and Corey Deans and these guys are now the big guys in the field was kind of back then students and graduate students and postdocs. These people actually, they came up with the idea, maybe there's a technical way that they can combine these things together. So efforts has been there sometimes before, but the way they came up with is that using the polymer that you can pick up these materials the successive way and just put them together and remove the polymer. I think this is a kind of rather many details that you have to go through. And later on that how to encapsulate, how to make the kind of context by etching it. There are many of the technical development actually was co-invented throughout this Columbia collaborations with my group, Jim Horn, Ken Shepard, and few of these PIs and the graduate students and postdocs belong in their groups. Just kind of put together this method.
I'm really curious. How do you do the gating or like the wiring of this multi-layer systems? Must be a big challenge.
Yes. So the idea is you have to put these samples. I think this comes with another film. Continuous films cover everywhere, but it's a flake. So flake, we are still using Scotch tape to make the flake. And it sounds like there's a very low tech, but it has a great advantage. First of all, it will give you the really high quality single crystals can be used into the device. Second, by just kind of choosing the right shape and right size of flake, you can just expose a different part of the layers that naturally that you can address from the top.
Nice.
Oh, so the gates, the electrodes only come from the top,
That's
but
right.
not on each layer you need them.
Yeah, but each of the layer that you can separately contact because their layers are separated out in different locations,
I see,
right?
I see. Just because of the special
Yeah. So if you want to do that with continuous films, that is huge development. You have to make the etch stuff right and these things.
So in terms of quality, CVD grown samples, are they still behind the
Still
exfoliation?
behind, yes. Yeah, that's why that if you are working on the scaling up type of device, CVD is the way to go.
Yeah.
But if you are interested in the kind of really deep into the science, high quality sample is important. Basically, Scotch.
Use this device.
Yeah, that's right.
This is your tool.
Yeah.
Does 3M ever use this in their?
Oh yeah. You can see that. Yeah.
In there.
There are a few blue tapes, stream tapes, and other things. So that was how the Columbia collaboration make this kind of next breakthrough, which is basically the way that you can make the heterostructures out of 2D materials and various different heterostructures and make the device. And this technique can be easily disseminated for the throughout the world and other groups, and this becomes now standard techniques that many people are using.
A bit of a tangent. You were mentioning that a lot of these scientists came from Bell Labs. Was this when Bell Labs was starting to fold?
That's right.
So it's the same reason why Harvard now has an applied has
Yeah,
sees.
yes,
Yes.
oh, that's
So,
right.
so
yeah,
Bella is
yeah,
basically
yeah.
split into Columbia,
That's right.
Harvard,
Yeah,
a few
yeah,
other
yeah,
places.
many places.
I guess, yes.
Yeah. So that
So
was
the legacy carries
that
on.
was a kind of somewhere in the 90s, late
Yes,
90s. I think
I
a
see.
lot of exos. Yeah, that's right. Yeah.
Or maybe one last thing on single layer graphene. So your group is also famous for doing this suspended graphene, which
Oh,
is
that was a long time ago.
yeah, this is a long time ago, but that's
Yeah.
like really difficult to do. Was
Yeah.
it to get cleaner measurement
That's
data?
right.
To
Yeah. So that was
be
approach
able
that
to-
the one way is that. I mean, obviously, then after integer quantum Hall, next thing that you want to do is do you want to get the fractional quantum Hall and even more exotic states. And quantum Hall is one way you can get the really exotic many-body physics there because, you know, that strong quantum conditions with many-body, that interesting things can happen. Quality of sample is important. So the one idea is, well, what if that we have this pristine graphene in the vacuum? What is best for that? So one try to make the suspended structures and that remove this the disorders from there. We indeed get this the first observation of fractional quantum Hall effect in such a sample, but practically making suspended sample is really limited. So efforts is stop somewhere. That once you figure out that how you can make the good quality of sample, not by suspending it, but encapsulating in the boron nitride.
I see.
Yeah.
How do you do that? Suspending graphene.
Well, you make the device on top of substrate and you etch away the underneath of the substrate by HF etching.
I
So it's
see, I
rather
see. So
simple.
you
Yeah.
remove this,
Yeah.
Like a channel.
Yeah.
Interesting.
Okay, then we can go to
What's
the
your
step.
What's your favorite Van der Waals material? Out of 2D material.
What do you think?
Yeah.
By now that we are working on many different 2D materials.
Yeah.
Still, I like the vanilla plain graphene
Okay.
because it's
Pristine.
interesting because everybody thought. I think that's naturally go to the next topic with twistings and those kind of things,
Yes.
right? Everybody thought the after novel, right? Graphene is relatively simple, right? That's why you want to go to heterostructures and all these things, right? Graphene is relatively simple and, you know, the phase space is limited. Maybe there are many other layers you can go through. But unlike the nanotube, where that approach is really handed over to the graphene and basically decay in the physics field, graphene didn't go through that similar things. Part of the reason is still the graphene, you can find a lot of interesting physics is in there. And even more, even with the graphene, that if you just twist it and kind of you go to the other type of stacking, still kind of there are a lot of things, even until today, that the community discovers a lot of exciting things in the graphene. And it's a relatively simple materials, but a lot of the corners, hidden corners, you can find it out. So I think that's why that I still feel like that, you know, after all 20-some years, I'm coming back to the graphene.
That's right. Is graphene already commonly found in consumer electronics? Did it make it?
Not that I know, yeah, but I know I have the first one of the first generation postdoc who went back to Korea, and he's the one that really specialized now growing the really large scale of the graphene.
Yes.
He's making kind of meter square type of graphene,
wow.
even longer.
Ooh.
A continuous roll of the graphene.
Yeah.
I think initially he wanted to use that for some of the electronic applications and kind of some semiconducting type of things. But because of there's no gap, it's not going to be easy. But I think the last time I just met him, he's using that graphene to make this graphene heater.
Oh, yes.
Right.
It's a good,
Yeah,
it's a good
and then
heater.
you can imagine that you just kind of coat your glass with the graphene, window
Yes.
shielding, and it's a very transparent. Or you can be very
Yes.
high quality heater. He can also demonstrate using this graphene heater for making graphene cooker. I think.
I
Yeah.
saw on Amazon that they are selling the graphene heaters, but I wasn't sure if they were correctly
Yeah, let's see that.
attributing that,
Yeah,
like if
let's
it's
see.
actually
Yeah.
one, if it's
Yeah,
one
yeah.
layer or
Oh
if
yes, and
it's
then there
like,
are many actually.
yes.
The claim the graphene included, I think, the graphene mask or those kind of
Yes,
things. I'm not sure how much graphene tooth brushes. I'm sure there are quite a graphene things, but I know that the Byung Hong, who is his name, his company's name is Graphene Square. I know they are making really real graphene product in there, and then seems like there are some things kind of on the surface. How much actually will be successful? This is way to see. But certainly there are some of now consumer products that comes around. Yeah.
And so far, mostly then for heating. That's like the one.
Right.
That,
It's not
that they
necessarily
already,
really high tech yet, but who knows? Yeah.
No, but that, but to start somewhere. Transparent,
conductors.
very
Yeah.
transparent.
Yeah.
Yes.
Because you see this ITOs, they're quite
rare.
rare.
ITO is the other thing. Yes.
Rare materials. And
it was initially the graphene attract a lot of the excitement in that way, but turns out the ITO is relatively cheap.
Oh, still. Okay.
Yeah. So it was it's a rather
tough.
difficult to beat the ITO in terms of the price
I
and
see.
replace it. That's what I was told. Yeah.
Ah, I see.
So how do you see the use of maybe 2D materials for the next generation of electronics, like transistors?
Yeah, that's a kind of hard questions. I think if you look at the semiconductor roadmap, they're usually toward the end of this roadmap. Actually, people are talking about the 2D semiconductor, like the TMDs, even nanotubes there. So certainly, at some point, the extreme scaling of the channel dimensions, you are being pushed to get into low dimensional materials where there's no surface-induced defects in there. That's natural choice. Whether this can be really incorporated with the modern electronics and optoelectronics, I think that's the way to see, because that required a lot of technological development of materials and processing and so on. But certainly there's always some possibility, I would say. But when it goes with this electronics and optoelectronics, silicon is always a moving target, right? So everybody thought, well, that silicon is that, but somehow it keep going there with up to the extreme, right?
Yes.
So how this will just kind of work it out, we'll wait to see. But certainly it makes sense that eventually the scaling this type of the 2D materials, 2D semiconductor can be useful, might be there. They might be useful in that the limit of the application. I cannot just predict more than that because it's not my field. Another part is that there are certainly kind of new physics. One maybe ever find out the 2D materials or engineered 2D materials. This may actually lead into the somewhat unexpected or maybe expected application, but this is kind of really far-reaching, right? Again, that's a way to see.
What about like silicon-based 2D materials?
There are predictions and maybe some experimental demonstrations, silicene, which is like the graphene, like the structure is made of the silicon.
Because carbon silicon, they have similar.
But because of the core electrons, it's not as stable as graphene. It can be stabilized only certain cases. So all this kind of row of the four, that silicene domain and those kind of things has conceived. Not sure that how much actually it can be stabilized and can be useful there, right? But certainly there are 2D semiconductors can be produced bit of the scaling of method like the CVD or especially MOCVD, right? So there are probably rooms that one can just go through that this 2D semiconductor route.
So in this periodic
they're in the same period.
In the same row, carbon is the most stable compared
That's right.
to the
Yes.
other.
Yeah.
I wonder if it's related to that life is carbon-based and not silicon-based.
That's a good point. I think that we need a new biologist. I think that some
We need a
biologist.
The thing is, if life were silicon-based, the metabolic product would be sand, would be like silica instead of CO2.
I remember that this one of the episode of the Cosmos by the Carl Sagan actually discuss about this type of life based on the silicons or something like this.
Because it's from the same period. Why not?
Yeah.
But somehow there are details which don't allow that.
Do you want to talk about the twisting
Twisted,
things?
yeah.
Introducing
Yeah.
a knob for another.
Twist and shout.
Yeah, yeah. I would defer that this twistronics the part of the year episode. I think you have the preeminent professor, the Pablo Javier at
yeah.
MIT, Graphene, and you can hear that really very interesting development. But this is a really
Yes.
huge development, and I think certainly the Pablo has a great credit onto these things, and then somehow really kind of believe and see through this one and developed, and that's kind of great story. But certainly that is a kind of new chapter opens up into this 2D material research, because it was a heterostructures or maybe different kind, but even same kind now. You have another continuous knob, so you can tune around to create this the structures. I think that's kind of amazing. So the probably that precursor of this twisting type of the work is probably dated back to probably around the 2010 or around the time. There a few reports, especially the people working on the STM, like the Eva Andre's group at the Rutgers, and probably some other groups that are working on STM, accidentally stumbled upon that this Moire structures, basically looking at the surface of the 2D material. Sometimes that some part of the crystal got cleaved and put in there and formed a moire. And then you can see that this kind of beautiful moire structures that reconstruct from the from STM image. That was kind of first kind of the image report in there. So it's been kind of discussed and known there. And around the 2012-ish, I think that a few groups, again, that by the just making heterostructures, that first heterostructure is graphene on top of the boron nitride, and that immediately improved the quality of the sample a lot. And that's a time that people just playing around there. Quite accidentally, I don't think anyone actually really targeted there, but graphene happened to be aligned very close to boron nitride, the lattice, and their lattice constant is rather similar, which means that when they're the low alignment angle between them, they can naturally form the moire.
Yes.
Right. But it was not initially targeted most of the time. And then when you just somehow, some of the device you measured, often you see the very weird feature start to appear in your transport. Yes. I think that is another like interesting draw that, right? So if you measure the graphene sample, usually people will see that it's something like this. So let's say that this is the resistance I'm measuring, say XX, and this is gate voltage I'm just changing. So gate voltage is usually changing the density of the electrons there, right? And zero density is where that so-called the Dirac cone is there. So there usually resistance is really high. So good sample, something like showing this. So measuring this, there's a Dirac cones there, and how sharp it is. Okay, you can see that in the paper, right? The sharpness tells you that how good sample is. Right? Yes. and then when the quantum Moire is happening, then there's something like this things happen. But in the somewhere in my lab, in the cases in 2012 or 2011, I guess, that we did some of this experiment on the boron nitride, and often that you see that something like this appears, right? And initially, when this type of things are happening, that there's just some mini Dirac cones there, which means that some part of your sample is really disordered and Dirac peak moves into there. This is not worth sample, just to throw it away, and then something's wrong with your device. And that was kind of initial feeling. But when you just put this under the magnetic field and just measure quantum Moire effect, your quantum Moire effect is really complicated. Quantum Moire effect appears. Your plateaus appears everywhere, and basically it's very difficult to figure out what is going on. So this sort of sample, that's likely the cases. Right? We almost throw that away until that figured out that there is not only one integer where the quantum Moire effect is governed by what is a lambda level filling, one integer. If I use a 2 integer number, I can explain why this quantum effect is appearing in this complicated way, right? So that comes out the basically the case that we start to see that there must be some things in here. And in fact, quickly that we figured out that is nothing but Hofstadter's butterfly. Do you remember that name?
Yeah.
Yes.
yes.
Remember that I mentioned the Paul McQueen that I just
Yeah, at the very beginning, yes.
Oh, you're a physicist. Right? That come back to my life, right? So was in some sense another very interesting moment that we got stumbled into this something that experimental data that we don't understand well, right? Some of the sequences, but just your data start to teach you that what is going on there. And then we start kind of open up this old paper of the Hofstadters and others. And of course, there has been some theoretical discussions that you can get the piece in here and you just come together and we can explain it, that there's no reason that we need a new theory. But nevertheless, that learn all these old papers and piece together and then explain the story, I think that was one of the rare moments I feel like that real satisfaction. Yeah, you know that your data start to teach you something, right? And likewise, this is not only my group's work, or around the similar time, Grimes group actually did similar work. Pablo groups actually did similar work. Anyway, so the community started to realize that the Moire pattern can provide something interesting into this 2D system, right? So that is kind of first the indication. So from there on, that people just look through that something that whether Moire can do some things, but it wasn't not a really major part. Hofstadter is interesting, but it's not necessarily really widely spread it out. So around that time that the 2010, there's yet another interesting theoretical prediction actually comes around, right? So there was the paper done by Alan MacDonald, and Alan MacDonald, his colleague, published the papers and stating that, well, if you have this two graphene layer that stacked into the very small twisting angle, there's a kind of particular Moire pattern create this superpolarity effect where you can make the band really flat. So that was kind of papers around the 2011 or something like this, around the kind of similar time. So I read this paper around then, right? And I was listening that this Bistros, he gave a talk, then I was kind of in his seminar. It was a kind of beautiful talk, beautiful idea. But again, I thought kind of, I think that's a relatively simple theory based on the continuum model. And I had a feeling that the theory is really, really sharply tuned, and angle is really sharp. So the chance that you can just get this such a kind of flat band with that sounds like a little bit more simplified. So I again kind of dismissed that idea, that kind of searching for those kind of the so-called the magic twist angle, that I just kind of dismissed it. Right? Now here it comes.
Now we know.
Where it comes out.
Yes.
Right? So few years later, that after I moved to Harvard, of course, I was in the same the research center that where Pablo is, and Pablo did postdoc work with my group, so Pablo and I just go really kind of well, and we discussed about some of this project, and quickly I learned that Pablo is working on this twisted the graphene sample. I was also working on the twisting, but not this magic angle, but much lower angle, where that you can see that now this Moire lattice becomes bigger, and there's some of this atomic reconstruction happen, and that will give you some topological edge states that make the network. There's yet another theory, which I feel like they're much more robust there. So I just kind of working on there, and when I just found that Pablo is working magic angle, I even just suggest Pablo, look at my data here. I think there's a lot of reconstruction is going there, right? So I think just Alan's theory, which actually do not include all these things, is too simplistic. I think that even if magic angle is there, maybe it's not the right angle. I think it's hopeless. But then I was completely wrong. So that was kind of the one interesting part. So I think that
So
How precisely
you
you
need to
need
get
to-
Pablo's perspective.
you have to really process your line that within is 1.1 degree.
Oh,
right?
wow.
So
Yeah.
away from, say, even 0.3 degrees away, you don't get the superconductivities, right? So it is really sharply tuned.
And how is
Yeah.
it done, the alignment?
Ask Pablo.
But do you
Yeah.
also do
No,
the
we do
twisting?
that. I think so. I think this method was initially that proposed that yet another group in the UT Austin, Emmanuel Tutuk's group, who first demonstrated how to the cut and it was tear and the rotating method. Basically, you tear the crystals starting from the single crystal, you rotate it and put it back. Was mechanical stabilities what determined that twisting angle, right? So that method was developed but was perfected by the Pablo's group.
So it aligns on the
yeah.
edges, basically. So it just depends on how you cut it, and then by itself.
Well, if it is single crystal,
yes,
you don't have to even just worry about these shapes, right? Because when you cut it, was your mechanical stabilities, right?
Yeah.
You cut it, lift it up, rotate it relative to the original one, that it will give you rotation angle, right? But if you just start to stack two different material, then of course you have to know that what is crystal directions. So that's yet another part. Yeah.
Okay.
I see. Anything interesting from different materials or so far?
Oh yes, I think that's a huge development in past what. Pablo's first discovery of superconductivity appears in 2019 or 18. I think it was 2018, I believe. Right, 2019. So it's been probably 5 or 6 years or something. Ever since that, this field is really again exploded even larger. So people are coming up with various different twisting. Graphene itself coming with various different twisting angles. Can be single layer, bi-layer, even tri-layer with a different twisting angle. Can be transition metal dichircogenide. It can be even cuprate, which actually we did. Also different twisting. Exciting part of the story is as we just kind of get into the twisting angle is yet another basically knob that you can engineer the different property into the materials. So it's almost endless the endeavor that people are actually trying out. Yeah.
And what are the criteria for superconductivity in 2D materials, so this twisted angle structure?
Right. I think one part exciting about this twistronics is the original demonstration. No one actually believed that graphene can produce the superconductivity easily. Part of the reason is if you just kind of think about any superconductors, basically you need a relatively large density of state to get this the higher TC into the system. Now graphene, because the carrier density is small, getting the large density of state is rather difficult. But now by twisting it, you can make the flat band where you can engineer the large density of state. So that's kind of one important ingredient to get into superconductivity. But it seems like it's going much beyond that. It is still not completely resolved that why the twisted graphene becomes superconductor. We know that density of state plays a role. It's a relatively low temperature. It's about 1 Kelvin. Or special cases you can make kind of few Kelvin, but it's not just kind of really high temperature. But the reason that this twisted graphene or to twisted system superconductivity can be important is it provides kind of model physics system one can study. So like the AMO system, for example, that somehow the model Hamiltonian provide you just look at the right physics. This twistronics or twisted system provide that engineerable system where you can test it out some of the physics there. So for example, there is the interplay between this flat band with some of the magnetisms and topologies, how those kind of things that create this emergent phenomena, including the superconductivity. And that's kind of really important topic. And since we have a lot of different knobs in this twist system, that allows us to kind of study about the physics in there.
So essentially you can control the band structures.
That's right.
By this
Yeah.
Okay.
Yeah.
And is there some intuitive way you could think of how that is conducive to forming Cooper pairs in the twisted.
Yeah, that is a really big,
Mm.
I think I wish that I know. I think that a lot of people have a somewhat different idea. So as far as I know, there are kind of two kind of interesting schools out there. One is that, of course, it could be still electron phonon, because electron itself, that their band got renormalized and flat band. Also phonon band structures got changes. And because of this one, there might be still very strong electron phonon coupling, which allows the kind of making this Cooper pair forms by phonons. The other school is now there are many other broken symmetry states, especially that could be spin or valley, the older states with the broken symmetry state. And this broken symmetry state has a generalized magnetism, may provide again the bosonic glue to glue down the superconductivities. So like the cuprate in some sense, there are still kind of several different scenarios kind of out there. Which one is a really winner? It's not clear. Unlike the cuprate though, in this 2D system, there are several knobs. Twisting angle is one. You can continuously tune the density. Applying the electric field, you can tune the band structures continuously. All these things give us a little bit of knob that we can test it out here.
Yeah.
Cool. Testing the SYK model.
Including the SYK model.
Yeah.
Yes, yeah.
I'm really curious to move towards the anion stuff, the topological.
Sure. Yeah.
Seems like it's getting pretty hot, especially with some of the... I brought the paper from this year, actually. From Microsoft, right? Which was...
Can talk about that.
Sure.
later.
Yeah. As much as I can. Yeah. I was quoted in the New York Times, and my wife was really proud of me. Oh yeah, your name appears in New York Times, because I was actually called up by and asked
to comment on this.
Comments on not in this paper, but people this paper, there are second papers also.
Oh, this is February 19, 2025. I think.
So this year, right? There's the previous papers.
So we can find the New York Times article. What you commented.
What was
the previous paper about?
Previous paper is a little bit more vague than this one, but also previous paper actually provided some technical breakthrough. They can now have the kind of reasonable device with a reasonable control of the disorder and demonstrate the protocol that how one can measure. I think that's kind of good protocol. I think they made another progress there. They start to see that kind of they can show that what is timing should look like and kind of what is coherence time should look like, and there are kind of progress. Whether these, I think certainly this is a lot of progress that compared with what used to be, really demonstrating engineerabilities of these approaches. To get into the really kind of claim that, hey, we have unambiguous demonstrations of the braiding and fermion parity changes, there are probably still kind of some more steps to go. Right.
Maybe just stepping back, you could just briefly explain what anions are.
Anions.
Anions.
Yes.
Yeah.
just a quick brief for.
So the typical way to approach the anion is that that usually quantum particles, quantum particles are indistinguishable, like the electrons. Among the electrons, they are not distinguishable, and protons, or that what other particles we know?
Photons.
Photons, yes, yeah. Those kind of the particles are indistinguishable, which means that because of this the symmetry of the indistinguishableness, when you just exchange those particle indexes, you actually encode this symmetry into the wave functions. And the way that you can just do that is usually when you have this double the braiding, the changing the name, that wave function restores some sort of symmetry, especially probably density restore the symmetry. So that will push that at least many particle that either when you just change this the particle index becomes positive, the wave function doesn't change the sign or change the sign, right? A very similar idea that going back to this spin half particles that we talk about Berry phase, right? And that's why, in fact, fermions is also spin half integers, and bosons, which actually is positive signs, that basically integer spins. So that is kind of something 101 of the quantum mechanics.
Yeah.
Now, once you get into 2D, however, there's other possibility. So what is the different 2D is this the exchange operation is often that called the braiding operations. Right? You just change this the positions, and this braiding in the 2D, if we confine the particle in the braiding, this braiding has the yet another topological invariant, which is winding number. So how many times you braid, right? So because of this topological invariant, mathematically that mathematicians figured out, in fact, there's other possibilities. Then you get this fermion and boson like the plus and minus sign changes. The wave function in principle that can have any phases that and especially if you just put the system right, I think this braiding numbers and the phases can be connected. And even exotic cases, when the ground state, the quasi-particle has a degeneracy, then after braiding, it doesn't have to wave function, it can just map to itself, but it can map into the different wave functions, right? So often that is called the non-abelian anion, and the Majorana fermion is one kind of this non-abelian anions. So these are all kind of mathematical description, which actually has been figured out in, first it was proposed in the 80s, but then there has been quite a mathematical, the theoretical descriptions.
Was Majorana the person who proposed them? Or?
No, Majorana was proposed a Majorana quasi-particle, Majorana particle as one of the fundamental particle in the 1930s. But this type of the anion is more like the emergent particle, condensed matter physics version, right? Majorana can be indeed one of the possible anions, but it's in fact the generalization of the anion is many more different type. Yeah, but then in the 90s when fractional quantum studies happened, and many of the first candidate of the anions, including abelian as well non-abelian anion, is proposed in the fractional quantum state quasi-particle. So that's kind of where that condensed matter physics get involved. But soon after that, and then it was realized also if you have the topological superconductor, in other words, basically the superconductor where the gap is in the bulk and the surface there is no gap. In this topological superconductor, when you create the defects such as the thread, these vortices at the center of the vortex or at the defect site, you can also create this the non-abelian anions known as Majoranas can be nucleated there. So there are examples that has been proposed over the time. Now, this actually gained that really excitement in the early 2000s when Alex Kitaev at Caltech proposed that if you're using this non-abelian anions, Majorana in particular, starting from the Majorana, you can, using this their topological property, basically topological property here means that once you're winding them, they are different states. So in a sense, they start this state, once you're braiding them, that becomes a topological object, which means that somehow these braiding sequences, you can encode these informations that's spread over in the space. And unless you're just cutting out some of this word line of this the particles, you can keep this the information kind of protected. So when Kitaev comes around this idea that using this non-abelian anion, that you can just demonstrate this quantum information processing can be done with a fault-tolerant way, it quickly gains much more attentions there. And ever since that, there are many different platforms that condensed matter experimentalists try to demonstrate it. Indeed, you can realize this anion, especially non-abelian anion, and one can manipulate these non-abelian anions to create some the demonstration of the quantum information processing in the fault-tolerant way.
And so I guess this is the Majorana 1.0.
Yeah.
The Majorana 1.0, and this is the follow-up. No, this one.
Oh, the follow-up. Yeah, that's the second one.
So this Microsoft efforts is actually done onto the one particular system, which is basically combining with a superconductor and semiconductor. And especially if the semiconductor has a strong spin-off couplings, then combined with the superconductor, you can engineer this topological defects, Majorana states, at a certain location by designing the device. You can manipulate this Majorana, and you can just braiding them and create this fermion parity changes in the system and detecting that or using that as your qubit. That's basically idea behind of that. This effort has been pushing around probably now more than 10 years or 12 some years, and there are few different approaches there, and it's now the efforts really, I would say, getting to industrial efforts, because to get into that stage you need to really careful control of the disorders and careful processing. So it's getting kind of beyond the academic lab scale of the operation. If you just think about how many people working in this the Microsoft team, that's a kind of order of 100, right? So many of the getting close to the quantum computing platform basically required now quite a bit of industrial efforts. Superconducting qubits is already kind of going well beyond the academic lab operation, right?
Which method do you think is most likely to lead to fault-tolerant quantum computing? I guess no one really knows.
I wish I know. Yeah,
because everyone's trying.
I think it's the fault-tolerant. I think this is more like the so-called topological quantum material-based fault-tolerant quantum computing is one way, but also conventional the qubits like superconducting qubits or called atoms, ions. They are not fault-tolerant, but they can basically kind of come up with this fault tolerancy by software, right? So I think there are various different kind of the efforts there. Who will be the eventual winner? It's very difficult to predict, right?
But the main issue with this platform is it like materials creating, is it like growing, let's say indium arsenide aluminum?
Yeah.
A kind of interface. What's the main challenges?
I think controlling the disorder.
Disorders?
Yeah, I think that's always the main challenges. I think it's all kind of quantum material platform. I would say that's the cases. Because again, you may say that fault tolerant means that it was resilient all the disorders. Yes, but within this topological gap, it becomes a fault tolerant, right? To keep it and make it large enough and that suppress this all the quasi-particle poisoning. There are quite of the control of the disorders is needed. Right?
What kind of disorders? Those?
The real materials, there is always a disorders, right? At the interface, there is a disorder. Unless you can control all the atom, right? There are always a defects, right?
I see. And in your group, you also do like probing of anyons.
So So we have the kind of two different platform that now my group actually involved into this anion type of physics. So one platform is more, I would say, traditional platform that fractional quantum Hall effects system. So as I mentioned, in the fractional quantum Hall, there's abelians and non-abelian anyons in there, and it has been pushed around in the gallium arsenide-based the semiconductor for many years, about 30 years, and there has been quite a progress as well. But graphene start to catch up rather quickly, and that's why I said that I like the graphene, because the quality of the materials is really approaching now, although it's scarcity produced initially, approaching to the what you can achieve in gallium arsenide, and there are a little bit of more flexibility in the sample. We can create the device in a much more flexible way, meaning that we can put all the gate controls, more sophisticated device structures. That will give us a little bit of advantage on the gallium arsenide, I believe, and that allows us now just kind of creating the anyons, including abelian and non-abelian anyons, start kind of manipulating and start to see that at least the way we can probe those kind of the exchanges, statistics of the abillions as well, now recently nanobillion. So that has been kind of one platform. The other platform is that combining with the superconductor with the topological material, topological insulator. Again, theory has been around on those systems more than 10 years, or probably about 10 years now. So it's not necessarily new theory, but nevertheless, I think quality of materials and the making the device progresses. So it's a good time that we can just see whether one can demonstrate some of the basic predictions from the theory, and going beyond that, whether one can kind of move into the range that demonstrating of the qubits out of it. Now, I personally believe that my role is more onto the basic science, which means that it's not necessarily I cannot just go into that industrial level of the demonstrations, but at least kind of basic physics work it out and kind of give you some sort of the bound of the how this materials and how that one can view that. I think that will be at least that I feel like there's something we can do in the lab scale.
But even within fundamental research, do you feel like the field has moved from more of a discovery mindset to a design mindset? Because now you have all of these tuning knobs. There's a lot of things you can do intentionally.
Yeah. I think it's both. I think certainly certain systems, certain part is there's more of the designing the experiments. That there's a strong theoretical predictions. I want kind of show this one and that part. But that's not all. If that's all, then I would say I would be a little bit disappointed. I think always there's a unexpected discoveries waiting even for that.
Most fun, yes.
This is a good example,
is the most fun, yes.
right? But not only that, as a condensed matter physicist, we have the other programs that going through that completely discovery mode, and it's not kind of expected things, but one can see that we don't know what it look like, but that's kind of some of the explore. So I think there are always kind of some of the balance that between design versus discovery mode.
Yes. Yeah, but I agree. Like the discovery part is always like the most exciting.
In some sense, I feel like the condensed matter, the really exciting part of condensed matter physics is it's often that big discovery comes from the serendipity. You didn't expect it, and just integer quantum or fractional quantum or right?
It's pretty good.
Surprises.
Yeah, surprises.
Good,
Surprises. Yeah.
I see. So do you see like maybe in the coming years, since we have these tools of like in data science, just try to explore or tune the knobs, as collect the data and try to search for some irregularities?
Yeah, I think I feel like that we are getting into a really interesting era in that regard, right? So we've been seeing that indeed that this data science and AI actually really powered up, right? Already I'm teaching this semester the condensed matter, graduate level condensed matter physics. I think really the part is how we want kind of eventually incorporate this AI into the educations, right? I think so. What is the best way of doing that? And same way in the research, I think it's a matter of the time indeed that this is a really the essential tool of our research. Maybe it's already right. The one interesting part is, I think the quantum materials or material research, we have only hundreds of the kind of order of 100 atoms there. But then you can imagine that how many different type of the system we can create it out of this one, right? We barely just get into the kind of ternary or quaternary type of the compounds. But beyond that, there are a lot of rooms there. There is no way that we can kind of explore all of these things. So somehow targeted research is important, right? I think that's kind of already going there, right? That what Google DeepMind is now, after they cracking all this proton folding problem, now they are looking for room temperature superconductor.
Yes, exactly.
Right?
Yes.
All of these things, I think maybe it's not a fantasy, maybe going there, right? I think who knows? We don't necessarily need a really fancy many-body physics, but simply well-designed electron phonon couplings into some materials, you may actually get into this room temperature ambient condition superconductor, right? I don't think that at least we have the theory say that's not possible, right? So I think these are kind of interesting moments, right? How one can just do that and how you can just couple with the experimental method of doing that. I think this can be interesting directions. One cannot just kind of simply go by how we can just crack where do we start. These are big questions, right? I would say that in the 2D material research, what we've been seeing before, at least I think going back to the what is a success mode of the Andrea Gimes and Costa Novoselov in the beginning, right? It was somehow they know how to fast screening. Right, where is a real single layer out of all this kind of the many layer and junks around, right? I feel like that maybe we are getting into the very similar mode. I think different scales and different way, right? Somehow that AI predict some candidates and many candidates potentially, and that if there is some automatic labs and create all these things, how faster you can just, how well you can just characterize and just doing these things. I think that's a interesting idea that a lot of us maybe actually start to think about. And maybe we are getting into a really different mode of the approaches.
So it's a combination of software side AI combined with robotics to carry out the measurements and screening.
Well, what is our role then, right? Right. That's a big part, right? But at the same time, I think when I just look at the AI and like the many others, I'm sure that this dissatisfaction comes from that, this is a black box to me. I think maybe problem gets solved, but I basically lose my joy that kind of figure things out, right? Something like the joy that I see that, this whole shadow data is basically 2 integer. I can explain that. I think that was a beautiful things.
The moment of insight.
I hope that somehow there's a way that we can keep that. Right? I'm not sure whether it's possible, whether our human brain is kind of catching that. But I hope that as much as possible, we can kind of follow through that. And maybe even that is something potentially still we can provide uniqueness, or we'll get to see. We'll get to see. Yeah.
If you had infinite resources, be it money or graduate students, is there a specific problem you would really like to work on that is resource limited?
Yeah, I don't think that I like the unlimited resource, unlimited things, because I know that because anyway that I have the finite bandwidth, I can just do that. Something that I can enjoy, right? At some point, my group actually size was really big. Something 20 something that I found my life becomes miserable. And a part of the reason is, that I think there are, if you have a lot of resource, a lot of the responsibility, a lot of other things, right? And I have the only finite bandwidth. I can just do that. Again, I don't want kind of have the black box. I don't want to have another paper just kind of being done. Something that I want to kind of learn things out of that. I think however small, however big a result it is, right? So it's not just something that kind of infinite resource and things, but I think that I wish to kind of learn things. Going back to this AI type of the things, robotic, and this is a kind of really resource driven, probably a lot of resource. Personally, I want interesting to watch that, but it's probably not me that I want kind of to push these things and organize this part. It's not some, even if in the end of the day that room temperature superconductor is discovered and it becomes rich and famous, I'm not sure that that's kind of something will give you the enough joy. I rather want
by understanding.
I rather want to choose that. Okay, so so that's kind of how you worked it out. That's what I missed it, or something like this, right? So that's kind of part. Maybe if I just kind of come up with some small methodology within my finite bandwidth, that's something that I kind of wish to have. It cannot be just done with infinite resource. In fact, I need a finite resource and finite time.
Do you think that the problems are getting more and more complex, so they need like complex tools, so it's difficult to find the solutions? Like all the low-hanging fruits are found, and now to get
but I guess that this is a part that the world becomes complex and complex, right? Each paper becomes really kind of complex to read, right? I think compared with what used to be. But nevertheless, I think this is again getting back to the our education and teaching type of things. That doesn't necessarily mean our undergraduate and PhD is not 4 years and 6 years. I think somehow that my concern is PhD also kind of tend to stretch it, right? Should not be. I think somehow starting from our basic knowledges to deliver to the front line of our knowledge, it should be in the finite times, right? So something like this. Say we follow through model of the current times, 4 years of undergraduate, let's say 6 years of the PhD. That we want kind of really reach the front line and get the meaningful result, right? How can it possible? Things become so complicated, right?
Yeah.
I think that's kind of where that is our way that we have to find out what is the shortest crack that we just get there, right? I'm just looking back at all this my undergraduate kind of old education. Yeah, it's all kind of useful. But there's no way that I can just fit all these things that special functions and all these things that kind of fit into educations within the short time frame, right?
Yes.
And you also need to learn something broad, right?
Yes.
So in some sense, we have to find out both the teaching, education, even in the research, what is a shortcut? We are not necessarily being the smarter. We have all kind of finite bandwidth anyway we can process, right? What is the shortest path we can get there? I think that's kind of probably even in this era of the AI and machine learning, this is something we have to figure out. And it seems like the phase is really fast, so we have to figure out fast. But somehow that's kind of what I feel.
And we need to
like.
do it without sacrificing, like there's a trade-off, right, between getting there fast and ignoring everything else. Because as you said, you did take field theory and then later on it was
so depth
helpful.
And the depth and the width, I think that how you
good
just
trade-off to figure that out.
These are all kind of something that, because in some sense our experience matter, right? Because this is something that we came up to here, right? So next generations, probably we want kind of think about slightly different way. And because we went through that, we know that probably, hopefully we know that what is shortcut that we can provide, right? Yeah. So that's.
And just recently there was, I think last week, there was a paper in Nature that described that people who really are masters of their field or great contributors of their field in adulthood tend to have had a very broad exposure earlier in life, so not necessarily the wunderkind types. So
maybe
it's really hard to make
if the human brain is still better than AI, maybe we can make a lot of long distance of the connections, and that's kind of where that if we're just doing the wild guess and those kind of things, hopefully that's something we are still better. Hopefully, where that aligns with the kind of very different experience throughout their life. I think that make it often just kind of make this wild connections possible.
That's cool.
All right.
I think it's a great grand finale.
I think.
Thank you so much.
This
That's
was
great.
amazing.
Yeah.
This is fantastic.
Very insightful.
Yes. No, now I know the full story.
Yeah.
We need to get the pieces from Andre and Pablo.
Andre, no, Konstantin.